Hello people, how's it going? Might wait a little bit for a few more people to join in. It seems like people are slowly trickling in. And then when we get started, essentially I want to make a fan controller for my OS. My BIOS, if I go in my BIOS, you can see on the screen here, I can change the fan settings for the whole machine. Like the fan idle mode, whatever. Basically, I want to be able to control that myself from my OS rather than having it to do it through the BIOS, because it's really frustrating to go through the BIOS. The other option is also to be able to go through and do that in Windows as well, so I can control it dynamically. So for example, when I'm away from home, I'd rather have my fans running at full, but when I get home, it's very loud and obnoxious to have that, so I like to turn them down. But I just don't like my computer running so hot during the, what's it called? During the day, if I don't need it to be. Still waiting for a few more people to trickle in here. I don't know how this time is going to work out compared to last night. I had a few people last night, not too many, but I announced this one fairly early, and hopefully a few people come in. So I probably will wait up to a few more minutes, and then from there we'll just go ahead anyways. So, I already have the BIOS pulled, and oops, computers, this one, BIOS. So this is actually a different version BIOS. I currently have 3.1 put on the machine, but ooh, what's this? Oh, that's my way of dumping it. I currently have 3.1 on the machine, but I dumped BIOS like version 2 or something like that, so that's fine. We'll just want to put a new folder here. We'll call this BIOS reversing, and to mark this as read only, because we don't want to smash over the file. And then let's just go and open this up in IDA. Boop. So this is biosimage.py. I've never seen that before. I'm gonna see how that works. I've never used. What? I've never seen that before. I did not know IDA could just manually do that, so I'm assuming that's at my FFFF vector, and it's already recognized that. That's kind of nifty. So BIOS E, that's gonna be sector. Where are my segments? Should be FFFFF or some shit segments. BIOS flash, yeah, okay. So if we look at BIOS E, go to the end, at FFF, that will be somewhere, our reset vector will be in here. Come on. Let's just see. FFFE. This should be a date code here, isn't it? Yeah. And what's this stuff? Okay, so here's our what? No, that's not our entry. FFFO. Control plus. Okay, I don't know why that was hidden, but yeah, here's entry point. But basically, since we already have the these strings to look for, this like fan idle mode and thermal and whatever, so that's what I'm gonna go look for. I don't think my kernel actually is compressed or anything along those lines, so we should just be able to go and search for that string. Fan idle mode. Oh shit. Well, that makes things difficult. Thermal. Catastrophic thermal event. Thermal alert. Oh, come on. Thermal error. Why is that not liking that? Thermal. quotes. Oops. Thermal, 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 thermal. But I don't see where this actually is listed, which is a little bit of a frustration. Ah, boy, that's gonna make things much more difficult than I was expecting. But that's kind of where the fun is, I guess. Sadly, I don't need the fan speed stuff too badly, so I can't say I'm gonna spend too much time on this if it goes poorly. Interesting. What about the setup utility? I've never actually done much BIOS reversing, so there's probably someone who knows what's going on here, and it's like, oh, you just have to unpack whatever. I'm sure this stuff needs to be unpacked in some way or another, unless it's Unicode, which would be silly. Nope. Non-Unicode? Okay. Well, that makes things tough. Next is we're going to pull that spec for my Super I/O controller. And I've already looked up SMSC Super I/O data sheets. I can't find the one for mine exactly, but this one's very similar, so hopefully we can just kind of piggyback off of this documentation. I think we have the like 34 something series. So if I just search for SCH HPZ600, let's call it, what's it called? Super I/O. It uses 5327, and we have the documentation for these 3000 series. I've looked a little bit for SMSC, this XX, and I just can't seem to find them. Element Sensors has a bunch of stuff on it, but what's this? 47252. This is different. This is Flash stuff. So I really struggled to actually find that one. So we're gonna just go by this one. It's probably similar enough. So it's got the same SEH in front of it, and it's just a SMSC Super I/O controller with all kinds of stuff. And if we just search for fan, here we go, temperature monitoring and fan control. So I know that my BIOS can properly set the fan speeds. I've tried Core Temp. Apparently Core Temp supports the Super I/O controller, but it doesn't work. My BIOS is able to set it programmatically. I know that when I've done some BIOS development before, the fans came on at full speed when I booted up, so the BIOS has to be responsible for actually slowing them down in the first place. So if we read through all this stuff, LPC interface, PWMs, and the tax going into the fan control monitoring stuff, HMI interface, blah 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 blah, located offset, blah 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 blah, base I/O address, device A, power supply, HPTR. Basically, I'm going to be looking through for some constants that I can search for in my BIOS, but I'm assuming that this BIOS might actually be packed in some way or another, which is really frustrating, because I've actually never worked with BIOSes, so I don't know how to unpack a BIOS, and that's a lot of work. I bet there's someone who has tools out there, but I like doing things from scratch. So let's see. Let's see how this goes first. Got the resetting the hardware monitor block. So I did a tiny amount of reading of this document so far, and somewhere it mentions that when the machine boots up, the power on reset, somewhere it talks about how the fans are running at full when you turn on the machine, which would explain exactly what I've seen when I've turned it on before without a BIOS in it, when I just have my own custom BIOS. And I'm just trying to find that again. Low power mode, temperature measurement, temperature control, fan control. Here we go. This fan control device is capable of driving multiple DC fans via 3 PWM outputs and monitoring up to 3 fans equipped with tachometer outputs in either manual fan control mode or auto fan control mode. The 3 fan control outputs X pins are controlled by a pulse width modulation PWM scheme. The 3 pins dedicated to monitoring this operation of each fan are the fan tachometer. 1 to 3 pins, fans equipped with fan tachometer outputs may be connected to these pins to monitor the speed of the fan. Cool. At power up, all registers are reset to their default values, and PWM 1 through 3 are set to fan always on full mode. Before initiating the monitoring cycle for either manual or auto mode, the values in the limit and configuration register should be set. So this is exactly what I've experienced when I've turned on my computer before. I've done a little bit of BIOS development. When I say BIOS development, I wrote 3 or 4 lines of assembly that would just make this PC speaker beep, and that's literally it. So I've done no more work than that. I've wanted to write my own BIOS, but after kind of researching the fact that a lot of BIOSes nowadays just take a binary blob from Intel to initialize memory controllers, kind of worries me. I don't want to use binary blobs. That kind of defeats the purpose of writing it myself. But nevertheless, this is exactly what I've experienced when I've been doing BIOS dev, is that that the fans come on at full speed. So basically what we need to do is we need to figure out how the BIOS turns the fans down initially, and if we can figure that out, we can probably figure out how to turn them up and whatever. So the fans are turned down before the video ever goes on, before the setup ever comes up or anything like that, or before any beeps. So it must be pretty early on in the stage. So while this video output that we looked for strings and none of them are present, so that might be compressed, but the fans get turned down very, very soon, so I'm assuming that that code's probably early on in the BIOS, and it's probably not compressed. This setup utility is probably compressed and run as like an ELF or something like that, just for simplicity for their development. So we can actually look for strings. You must log basic. What? Infineon. That sounds familiar. Infineon. Semiconductor, okay. IFXTPMDRV. Seems like some sort of driver that's stuffed in here. What is this? Someone just has this on a website. This looks like it might be BIOS, actually. FXTPDRV. MA, yeah, that's our string. Huh. So if at the end, does it say compact? No, it doesn't. Oh well. Funny what you can find when you're looking for these strings. IFXTPM. TPM. Trusted computing? Interesting. That'd be fun. We should go find a trusted computing vuln. That would be a fun thing to do at some point in time. But sadly, that's probably going to be too valuable to do on a stream. Don't know if I'm gonna go find TCMO days or TPM. So here we can see it's doing. It's at least got strings for DMM stuff, ECC stuff. So it's doing memory, more IOH stuff, setting up VTD in theory. So it's doing a lot of stuff prior to any decompression. So hopefully we can find some information about our fan speed stuff. Taco. Where's that? Taco. Taco, taco, taco. Taco, 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 taco. Is that a coincidence? Someone actually putting... Is that like someone's special magic taco? That's kind of neat. I like it. BCP, CMP? I don't know what that is. Nope. No idea. Watchdog timer, QPI 0, status, error, link layer, physical link layer. JTAG tab port. There we go, IOH. I think if we go back to that spec, I think this guy, what page are we on currently? We'll just copy this string so we know where to go back to. I need to figure out what bus this device is on. And watchdog timer, we saw that before. I'm curious if that kind of relates to this. General description. Super I/O device, LPC interface. Is there anything here with LPC? Nope. Let's see if SCH is present. I'm just going to be looking for some of these strings. Probably look here as well. SCH, no. Oops. What about LPC? I'm actually not familiar with LPC. Oh, fuck off. Nope. PME Wake Up Advance. RSM RST? Sounds like, what did we have? BCM CMP. PIR. I'm just looking for something that corresponds between these two things, and hopefully we can get a quick start just by going off of a string. Thermal alert. That could be interesting. This might not use thermal alert in... I wonder if this actually calls something thermal alert. No, it doesn't. Thermal zones. 1, 2, 3. Let's go to where this is. Let's find references. And thermal alert. Any XREFs to here? Okay. Is this being used in a lookup table? It looks like this is inline. Whoa. It looks like it's inline. Nah, this isn't inline. These are actually pointers here. It looks, yeah, these are definitely pointers. Data, yeah. Damn it, Ida, why aren't you doing this for me? D. There we go. That's frustrating. Okay, IOH config, parity error. TS max, updated, catastrophic thermal event. That's what I want. What did I eat for dinner? I haven't eaten yet. I just haven't felt actually too hungry. I felt hungry and then I didn't feel hungry. So I don't know why that is, but not sure. Okay, let's see. 3 pins dedicated to monitoring the output. Registers 54 through 5B. Question is, how much of this shit has been properly disassembled? Doesn't look like any of it. What a load of ass, Ida. You're so useless. Okay, start, jump, CLI, move, BP, this. So it's setting up a temporary stack. Loading a GDT, CR0. This is setting protected mode. So this is, yeah, really. So we boot up, CLI, set up some shit in BP, then we immediately load a GDT, we move CR0. So this is setting up protected mode if I'm not mistaken. I think that bit 1 is protected mode, control regs, yeah, PE, that's protected, oops, yeah, PE here, just protected mode. I think Wikipedia actually has this if I just Google CR0. CR0, protected mode enable. So I guess the first thing the BIOS does is get the fuck out of 16-bit mode. Pretty interesting considering it drops back down to real mode when it calls you, but whatever floats your boat. Then we do a far jump into 958A, but which is here actually, so we don't actually have to look up that segmentation. But say 0 and X, DSX, ESX, so basically this is our GDT here, if we look this up, and the format of a GDT should be GDT, come on. GDT, it is 64 bytes each. So if we do DD, 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 D, unless this is code, that actually looks like proper code. We're ruining things, everything's breaking. Broken it. That's not code. Okay. Code segments, this. So this has to be... Ah, fuck, I'm an idiot. LGDT is going to take in the word followed by a D word or vice versa. So... which one makes most sense? I think that makes the most sense here. If we go here... Nope. I think it's word followed by D word. And then this is code. So this should... That doesn't seem right. That doesn't seem right. Okay. Dev, osdev, any of these should do boot BSP. Doop, doop. Let's go load GDT. GDT format is in this format. So we have a word, which is the number of entries, or the size of the GDT. Yeah, that's correct. So that's the size of the GDT, is that many bytes, and it's -1, which is why you have 287 here. And GDT base. So this is correct. I don't know why this address is fucking rude. So that's a frustration. Load GDT from code segment. Is this actually this? I don't know if that's right. We're kind of grasping at straws here. Oh, that looks... C3FA? That looks relevant. C3... Yeah, this definitely looks like it's GDT. Okay. Do. And that's... How big is that table? It is 287 hex in length, so 288 in length, 648. That's fucking nuts. That's 81 entries? That doesn't seem right. But it looks like that is... this does look to... Fuck, where were we? Wait, how did this work? Where did we go that this worked? What? I went somewhere that made sense, and then now nothing makes sense. So another place, GDT on this. What did I do? What did I do? Where did I go? Seriously, I went somewhere that looked relevant, and now everything's ruined. I've ruined everything. FF3C9. Well, I don't know how I managed that. Can we find where we were? Oh my god. There we go. F2EE. How did I get here? Because this looks like more... Load GDT. Loading it from code segment. This is apparently the pointer to the thing. And maybe it's a problem with IDA. If I extend this FFE. Nope. Haha. I have no idea what I'm doing, do I? Okay, whatever. We're gonna jump to this location. Hopefully this will just resolve. It did. And then put 30 in all of the segments and pop EAX. Where do we set of ESP? There's this call where we Oh, that's our return address. Yeah, that's how it's working. So this is PS2 shit here. Then it jumps back to BP. Pop BP. How is it doing that? Where did it set up a stack? I don't remember it setting up a stack. Jump. Jump. Okay, whatever. So we jump there. Ends up returning, or this is where it actually jumps to. All that's doing is setting the code segment, so none of the code segment is correct. And with FE, so that's getting rid of protected mode? What? Move EAX00 and AL with FE. Move what? So now it's exiting out of protected mode again? And then it's jumping here. I have no idea what's going on. Okay, then we jump to BP, which was set up. Last place that was set up was here. So this is where we're going to continue execution. Code, yes. Okay, and then this is going to call this byte swap on that ABCD. More stuff here. CPU ID, read MSRs. The question is, should we be actually reading through this, or should we just be looking for anything that operates on some of these magic numbers? But there really aren't many. Why is Wikipedia still loading? Okay. Where did that spec go? Did I close the spec? Fuck, I'm an idiot. No, here it is. Okay, so registers 54 through 5B. Device startup. Now keep in mind this is different spec than, or this is a spec for a different chip than what I have. I'm just assuming that most of these things will line up. If the temperature zone exceeds maximum limits. The issue is these registers are not going to be the same ones that you just do ins and outs on, so I can't just look for ins and outs that actually operate on those. Or maybe I'm wrong, but that is going to be my assumption for now. What I want to do is I want to find like a 2 or a 4 byte magic number, and I can use that magic number to try and find where the stuff is actually being used in code. But sadly, I don't see any. Oh, you little shitters. Slow interrupt disabled. Could look for this, but that's going to be present in too many locations. FFE. FFE. Ooh. Hardware monitoring register set. Fantac. What we need to do, yeah, default value FF. That's, what is this? Only writable when the associated fan is in manual mode. This case register is writable. And that's maybe why speed fan's not working, is it's not in a writable mode. Temperature shit. Pedalium shit. Ooh, device ID. Device ID. So how do I access these registers? This is all I need. I need to find a way that I can get access to these registers. And once I have access to these registers, I'll kind of know what's going on. But I mean, I can't search for 3D. Like, there's just no fucking way. I could do a text search for 3D. Yep. And yep. Oh, fuck. Where is 3D in this line? Oh, here it is. Nope. 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 3D09. If only there are some more fucking magic numbers. 3DFE. But sadly, none of these seem to have any settings. So let's try and read this from the start. There's going to be some way of detecting this shit. IDA, 8 serial pins. So how do we communicate with this bitch? LPC bus interface. Yes, yes, yes. Functional blocks, reset generator, serial ports, PCO, GPIOs, hardware monitor, blah blah blah. This kind of looks like VTQFP. Oh, why is copy and paste not working? Oh, fuck off. VTQFP. Yeah, this is what the chip looks like. It has this kind of rectangular shape. I haven't counted the pins on it, but this one seems to be as rectangular shape as well. So, yeah, blah 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 blah. More shit, more shit. Let's actually fire up a PCI device lister on my system, just to see what PCI devices are present. Somewhere we have PCI dump. Oops. Here we go. Oh, is this on a... That's on a laptop. So we want to get PCI dump shipped out. Oops. PCI dump.asm. We need to make this Pixie bootable, so let's pull that from here. If def Pixie, bloop, and let's do fine Pixie and CD into here, and make fbin piece PCI dump.vfd, actually oops, PCI dump.asm, that built, take this, we're gonna throw this in Skeletor, because this is where we're already having our Pixie shit boot from. So if we just reboot this machine, that should come up, grab that Pixie image, and we'll see what PCI devices are. So maybe this is accessible through PCI, but I'm assuming it's not. Oh shit. So we'll see. PCI. So we have all the status register shit, but it did say this LPC bus, so I guess we can Google that as well. But okay, there are a lot of devices on this thing. Shit. And you can see it overflowed to the other side of the screen, essentially, because my thing is only meant to display a certain amount of things. LPC bus. Low pin count bus. I'm gonna grab a sip of water 1 second. Okay, cool. So we have this LPC thing. This is very much so mentioning exactly what we have. I say bus. So basically, how do I, maybe osdev has something on it. Alright, able to accept IO cycles, osdev LPC. Someone's probably done work on this, and we can kind of borrow some code. LPC is for legacy devices. It's almost transparent. You just access them with well-known I/O ports. Yep. So we're not doing ACPI because fuck that. OS gathers information from BIOS via ACPI. Question supported the BIOS gets these. Of course, motherboard vendors know how things are wired and just hardcode the tables in their BIOS. That's great. LPC, ISA. Okay. How do I interact with the LPC bus? That's all I want to know. PCI, LPC write DSDT. Oh, beehive stuff, that's kind of fun. But that's not what we want. DSDT says, is this performing a write by using the DSDT? Because there's no way I'm going to do that unless it's writing the device in the DSDT. God, really? How has no one done this? Bus device driver. Windows driver development. LPC and PNP. ISA bus, so maybe I can just access things on the ISA bus. The other thing I can do is I can look up the PCI, what is this, SMSC PCI vendor. We can see if there's a vendor code. Oops. And 1055. 1055, do we see that anywhere? 8086. Do not see that unless it went off the screen. But I don't see it there either. 10, 8086. Those are all 8086. Okay. And those aren't. We need an ISA bridge. So I'm assuming if we go to ISA, we can communicate with this thing. I've never done ISA work before. Or maybe I have. No, I don't think I have. One second. Eating a cookie. Sorry, I mute my mic when I'm eating cookies. I don't want to annoy you people with crunching. Okay. ISA. Let's see if the Russian wiki page has more information. All this stuff is saying the programmer doesn't know about it. I want to know about it. All I need to know is how to get access to these fucking regs. So somewhere, all these registers that I want to access are just present. What's this? Pin functions, all this shit. Looks like it has a parallel port on there. GPIOs, there's a lot of GPIOs in here, so that'd be kind of fun. But this chip also has block diagram. Boom, boom, boom. Got the UARTs. The thing is, these will register the so let's see. These guys are. We got some UARTs on here. Parallel port shit. LPC bus interface. So that's where it must be talking. Power management, GPIOs, MSC proprietary compatible floppy disk controller with digital data separator and write pre-compensation. Yeah. Oh, what do you work on? Oh, I work on the SMSC proprietary 82077 compatible floppy disk controller with digital data separator and write pre-compensation. That is what I do for a living. Who fucking names that? Okay, reset generation watchdog timer. So it sounds like I can also generate resets through here. We got the keyboard and mouse controller through here, as well as the 8020 or 820 line, A20 line that you can set. So basically, all of this stuff seems to not be something you. It's something you don't. It seems like all this stuff, like the keyboard, mouse controller, all the UART stuff, is controllable with typical I/O stuff. So somewhere those are getting remapped. Either they're getting remapped or they're just mapped like that from the start. Which means I might actually not have to talk on this SMC or IMA bus or whatever the fuck it is. It should just, maybe it registers some IOs. Let's see, LPC interface. Host processor interface. Host processor communicates with super IO features in the SEH311X series, blah blah blah, read-write registers in the LPC interface. Port addresses, these registers, okay, we'll want to look at that after this. Oh, that is this table. Register access is accomplished through IO cycles or DMA transfers. That's what I want. I want this. What IO do? How do I do IO? Okay. So you got the serial ports, COM1, COM2, and that's correct. You just do like the base, I think it's like 378 through 37F. So that like makes sense, but what is the base? How do I know the base? Because somewhere this probably has configuration stuff, floppy disk, keyboard 60 and 64. So these are like absolutely hardwired to 60 and 64. If you're not familiar with keyboards, those will use the 64 IO port. Another thing we can do is just bring up the device manager and bring up the fucklaroo where it shows us resources, all the IO stuff, and maybe we'll be able to draw some connections here. So 60 and 64, you can see 64 is mapped to PS2 and 60 is mapped to PS2, and you can see that's just hard-coded here. So this is what it's talking about. So somewhere these base addresses are configurable, reserved, but none of this mentions how I access the SCH stuff for, so LPC signal shit. I think this is more hardware level stuff. LPC cycles that are supported. IO read write, memory read write, DMA, bus masters stuff. So IO read writes. Okay. So here's is talking about, primary addresses. So this is like obvious. So it seems like this is sitting on a bus and ISA just goes out. So the ISA, this probably just sits on the ISA bus and it basically steals these ins and outs as they come through, which, I wish I had more visibility into what was going on at a physical level on these things. I'm slowly learning, but it's not very well defined. So that was explicitly talking about ports. What I would love to have is arbitrary ISA. If I had arbitrary ISA, then I could talk to all this shit. So this is all floppy crap. So let's actually go to the index and find the next thing after floppy. UART. Blah, blah, blah. Is this going to talk about the ports? I'm basically trying to learn how this documentation is written. And when I learn how the documentation is written, I can try and figure out how to read the other documentation stuff. Blah, 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 LSR. Yeah, this is all. Where's the fucking port? Default. Baud rates. Whoa. Whoa, what are these modes that I can do? Can I really do 1.5 million baud? Why am I not doing that? Okay, that's kind of cool. Anyways, that's for future stuff. Register summary. Yeah. So these are offsets on the base, of course. But what's the base? We know the base is going to be 378, but I want to see where it's written in this. Somewhere I want it to say the base is here. But this documentation seems very inconsistent. Fuckers. This is all like base address. How do I set up the base address? Refer to configuration registers for information on disabling power down and changing the base address of the parallel port. Okay. What was it? Configuration registers, I think. Config regs. It's very flexible. Ooh. Based on configuration architecture plug and play. Flexible resource, blah blah blah, allows the BIOS to assign resources at post. Of course, after PCI reset or VCC power on reset, it's in a run mode with all electrical devices disabled. Electrical devices may be configured through standard I/O ports, index and data, by placing it into configuration mode. Okay. The BIOS uses these configuration ports to initialize the electrical devices at post. The index and data ports are only valid when it's in configuration mode. Strap options may be added to allow 4 base address options. Okay, those ones, and at the deasserting edge of this. Okay. Index IO base bits a base address. Why? It's saying the index and data ports are only valid when it's in configuration mode, and after a PCI reset or reset, it's in run mode. It may be configured via placing it into the configuration mode. Okay, configured through 2 standard configuration I/O ports. How do I put it into configuration mode? And let's see, configuration address ports. To be controlled by these pins. Question is this hardware control? Is this software controllable, or is this all hardware? Entering the device enters the configuration state when the following config key is successfully written to the config port. Config key 55. Why is that not a bigger number? 55. Device exits the configuration state when the following config key is successfully written to the config port AA. So what is the config port? The config key, configuration mode. By sending it to the config port. Oh, wait. Where did it mention 2E? Okay, that is the config port. Sweet. Look at this. So easy. That's all I have to do. Why didn't I just read this code earlier? Oh my god. All right, time to brick some shit. So we can put it into configuration mode, and then when it's in configuration mode, we can do this stuff. Oh ho ho! Oh ho ho! Oh ho! Wee wee! Oh ho! Primary base. Yeah. Serial ports. You know, I keep thinking I'm in the context of doing BIOS dev where I don't have RAM, but I will have RAM, because I'm going to be doing this at OS level, which is fucking magic. So I'm looking through these. Basically, we get to control a lot of stuff. We can control the serial port register stuff. Okay, chip level, global configuration. This lies in the address range of 0 to 2F. Okay, so where does this start? 30. Okay. Let's see. Automatically clears this after a write. Device ID, hardwire, device revision, configuration address, default, test registers. Reserved. You should not write to this. It may produce undesired results. Oh, that's tempting. Electrical device configuration registers. So this is like I/O based stuff. Okay. DMA channel select. Floppy disk controller, parallel port, serial port, keyboard, security key register. Ooh, I wonder what that is. Serial port 456 config ports. Primary interrupt select, DMA channel. Okay, so let's pull this spec up in yet another window just so we can have two things at once. Let's bring up the thermal stuff, where the shit that was, fan control, and let's do input monitoring, low power mode, fan control. So we control the PWM outputs, and we do this via the 3 PWM pins, and these are the limit and configuration registers are 54 through 5B for the minimum speed on that. Okay. So I'm still not sure how all this stuff works, so let's try and put this device into configuration mode and then read out from it to get confirmation that we've put it into configuration mode. Once again, since this stuff is all in since this is a different spec than the chip we actually have, there is a chance that this might not just directly work out of the spec. So what we're going to use is we're going to use this spec to get a general understanding of how these Super I/O chips work. Then when we understand how Super I/O chips work, we can try and find the actual correct values in some other stuff. Yeah. I'm going crazy right now. So let's, I'm going to quick put a little patch in here. Let's call this Super I/O. Actually, we'll make a whole project for this. We'll be spending enough time that it's worth it. Super I/O, let's plop this in here to make a make file. We're going to only do this OS currently in 16-bit, as we have no reason to do it in any other mode. SMC00, that's a make file. That is not a make file. And we'll do nasm bin super io.bin for the output, and super io.asm as input, and let's just delete super io.bin every time. And this is to start, and CLI or AXX move ESX ESDS FSGS SS DS FSGS SS move SP OX7000. Let's actually do 7000 just to make sure, and then jump AX or unland halt, and okay. We'll do CLD just for good measure. I'm trying to get in the habit of using CLD. If you're not familiar, CLD clears the direction flag, which is part of E flags. If you don't have the direction flag cleared, if you do STD, that will set the direction flag, which means that when you do like a rep STOSW or rep STOSB when you're doing a string operation, instead of going forwards, it will actually go backwards. And I've never actually seen that set when you enter, but a BIOS, I mean, BIOSes are pretty shitty, so never trust them. Okay, so let's just halt here, jump short, dot halt. So we have a little basic OS here, and now we can, we'll just copy their code exactly. Move DXOX2E, move AXOX55, out DXAL, and then let's also move AXOX, what was the exit mode, and out DXAX.AL. So basically, we'll put it into config mode, and then we'll take it out of config mode immediately. Yep, that's okay. That's correct. And now that we have that, we want to... Hopefully there's some way that we can get information. So let's actually try and poke one of these serial port things and try and get this to print out 3F8. If we can get 3F8 out of this, we know that somewhere... Basically, if we get 3F8 out of this, we know these registers are lining up with their specification. So we're just trying to get hints on this. Blah, blah, blah. Okay. God damn, it is really warm right now. Serial port. So how do I actually... So these are the indexes for the global configuration registers. PCI resets. Are these the values that are on different resets? Configuration, port, address byte, low byte, high byte. So let's actually... What was their code doing? It was doing a configure register CRE0, logical device 8. So 2E, it outputs 7. So it writes 7 to the point to the config reg. So where's it pointing 7? What does 7 mean? It's writing 2E. It's writing 7 to port 2E. 7. Logical device number? Okay, yeah. Point to logic device number config reg. Then point to logic device 8. Oh, this is writing to 2F now. So basically you issue a write to tell it which register you want it to point to. And then you issue another one to point it to something else. And this does point it to CRE0? What? Let's see, E0, what's that? Is E0 on this? Oh, this spec. Once you get to understand these specs, everything gets a lot better. E0, logic device configuration. Vendor defined. Okay. Maybe I should actually read instead of using this assembly stuff. Somewhere. Configuration mode. You set it into configuration mode. It activates desired logical devices in... Enter configuration mode. Place it in configuration mode. Send the key to the config port. So this is config port. Define config port as 2E. And just to be extra verbose, we're just going to do this so we know what's going on. So we're writing 5.5 to the config port, then we're writing A to the config port to exit. It returns to the run state. Those are the only two states. Okay. Once the configuration key is received correctly, the chip enters the configuration state. The auto config ports are enabled. The system sets the logical device information and activates desired logical devices through the index and data ports. In configuration mode, the index port is located at the config port address, and the data port is at index port +1. So I guess the terminology changes. It's the same address, but this is now no longer the config port. This is called the index port. Then we have a data port, and this is 2F. So, okay. And this is, let's make some more defines. We'll define start config key, OX55, and we'll make one called AA. We'll call this end config key. We're just doing this so we know exactly what's going on. So we're writing start config to the config port, then we're writing end config to the config port. And when you're in config mode, we now no longer use the config port, we use index and data, which are the same ports, but they're just named differently. The desired configuration registers are accessed in 2 steps. Write the index of the logical device number configuration register to the index port, and then write the number of the desired logical device to data port. So write the index of the logical device number. Write the index of the logical device number configuration register to the index port. An example, okay. Write the address of the desired configuration register within the logical device to the index port. What? Write the address of the desired configuration register within the logical device to the index port, and then write or read the configuration register through the data port. Okay. So, we are going to do move DX, the index port. We're going to move AX, OX x07 out dxal. And then we're going to, so we've written the logical device number configuration register. Right? 7, logical device number configuration register. Okay, so that was the first thing we did. And now the next thing we do, so this now is read-writable, and let's now write the index. Okay, now we want to write the desired logical device to the data port. So move dx data port, move x ox. So let's go find a device that we want to configure. Write the number of the desired logical device to the data port. Number of the logical device configuration registers. So global configuration registers, then logical device configuration registers. How do I switch between the different logical device 0? Oh, I see. So this is 0, this is 1, this is 4. So let's number 4 should be out dxal. This should, now we've said we want to talk to logical device number 4, which is the serial port. Now we're going to want to pass more shit, which is going to be the right in 2 steps. Now we write the address of the desired configuration register to the index ports, and then move AX, OX, whatever, and then read or write the configuration register through the data port. So, serial port number 1, and then we want the primary base IO address high byte, primary base IO low byte. So that's what we want to do. Let's read that. Let's read the low byte, which is 61 out dxal, and then we'll do a move dx data ports, and then we'll do an in al dx, and then we'll move a h ox of 30 or of, and then stow. Here we'll actually set this stuff up. Move di oxb8 100, move esdi zor di, move ax ox03, int ox10. So if you haven't seen me doing osdev before, this is set video mode to 80 by 25 16 color. This is set up esdi to point to the screen buffer. So this is basically saying I want to query the low byte of the serial port. We input that, then this AH is saying AHOF means set the color to bright white, and then we store AL. We actually need a hex print function. Let's just write one quickly. We could borrow one, but I don't know if I have a 16-bit one, so let's just do out hex 16. And so let's make a lookup table quickly. So so a hex slot is going to be db 012345678 you see def. And then here we'll say this will take in dx, that will take in the word, or 16-bit word to write to screen, and then esdi will also be pointer to location on screen to write. And now what we'll do is we need to print off one nibble at a time. Let's do move x dx. So let's do loop move cl4. We're gonna have to loop 4 times because we have 4 nibbles. Rotate left by dx by 4. So now what is the high nibble is now in dx move x dx and x with F, then move BX hex lot. We can actually do that above, and we'll do that here, and here we'll do move AX BX plus AX, and then so this is just byte, and that's AL and AH, and that with that. Correct, that's good. And then this is dex CL jump not 0 short dot loop ret. I think this will work. It's not the most compact code, but it should work. And then we're smashing here push x push cx push. DX is fine because that gets rotated all the way around. X and BX gets smashed. So let's do pop CX, pop BX, pop AX. So we get hex lots, we move CL into 4, that's our count number of nibbles. Rotate left by 4, we swap that over so we can mask off the nibble. Then we move AH because that's our color, and then we do a deref off of BX plus AX that will look up in our hex table, and that's not exploitable, and it doesn't matter anyways because we don't care. So that should print out the character to the screen, decrement, jump not 0, loop, and then we pop everything off, and ESDI gets smashed. So I'll actually do this syntax here. We'll say updated, and so let's say smashed, and this one is not smashed, he's retained. Okay, so then we should be able to here move DX AX, move DL AL, XOR DX DX, call out hex 16. And that will print off, hopefully, that will print off 78. So let's build that guy. That's the wrong OS. Use super IO and make invalid effective address. BXAX. What's wrong with that? What is wrong with that? BX is a valid. We can index off of BX, that's not a problem. What am I doing? Valid effective address. Pretty sure you can. Well, that's fine, right? X, CX, DX. Because you can deref BX. Fine, we'll just add it here. So we'll do an add. Oh, fuck, no, there's a way of doing that. What am I thinking? I can do the lookup table thingy. What is that on x86? Dev specs Intel, oops, specs Intel instruction. There's a really nasty instruction called xlats, which is, you'll see in a second. Look up, set AL to memory bytes, EBX plus unsigned AL, xlat, B. Okay, and we'll just do that instead. Problem solved, bitch. Okay, now we need to go into our DHCP server and make sure that we're shipping out the right file name. We also need to set the correct path here. This is now going to be in super IO. Done. And this guy, DHCP, policies, scope options. This needs to be named super IO.bin. And what we should find is if we shut down this machine, it will now boot up into that OS. And what we hope to get is, so So we got the low byte of 378, so we want to get 78 on the screen is what we're looking for. And hopefully we get that. And then we take it out of the mode, and then we hold forever. Come on. Come on. This is hopefully gonna work. Otherwise, it will be a complete failure. F8. We get 3 F8. I lied. But yes, that's correct! It works! Everything works! We're so smart! Oh my god! Man, usually this always fucks up on my first write. So I wrote all this code and it works. I'm so proud of myself. So if we go pull the other part of this, let's store this into BP. So let's, actually, fuck, that's not gonna work well. Let's do CL on this. And then we will do this again. So we're still in config mode. So we save off low byte into CL. And then this, we're gonna get the high byte, I think, is 60. Let's pull this. 60 is the high address bytes. So let's do this. We'll save this off into CH, AL. Save off high byte into CH. And then we should be able to do a move DX, CX. And call out hex 16. And then if we boot this, we should get the full 3 F8 to print on the screen. And if we get that, that means we know what we're doing. Eating more cookies to celebrate that this is gonna work, and we're super smart. Look at that. Look at that. Real mode assembly is the easiest thing in the world. Okay, so now we got that working. So let's figure out how to access those fans. So logical devices. So these are logical device configuration registers. Let's see. Oh, thanks, Firefly. I'm glad you're enjoying this. I mean, it's kind of a small crowd, so it's not too many people to please, but a lot of people like my silly high energy and excitement over the stupidest things. I just love this stuff. Like, I've been doing this for basically ever since I was like 14 or 15. OSdev has been my passion. Okay. Now we want to figure out how to do this fan control. So, limited configuration registers are these guys. And, so how do we... These are the global configuration registers. So the limit and configuration registers are these. The limit and configuration registers are defined in PME status 1. Let's see. Let's trying to find this PME status 1. Oh shit. Oh no. Oh no. We refreshed it. We've lost everything. We've lost everything. Where's my panic button? Oh no. Fan control. Okay, we're safe. Whew. No one saw that. Okay. Primary keyboard interrupt. This is so cool. Like, I'm gonna be able to, like, rebase all of my I/O ports. I'm like, oh, I'm gonna put my serial port at this random ass address for no reason. And then there's gonna be some person coming across who's, like, done OSDev before, and they're like, didn't you know that? Isn't this just obvious? It's OSDev 101, you idiot. And I'm like, okay, fine. Okay, chip level, SMSC defined, device ID, config control. Okay. And reserved. Configuration address byte 0, configuration address byte 1. Is that... Limit in configuration registers. At power up, all the registers PWM 1 through C are set to fan always on. We need to... So like these registers are correct, but the thing is like I'm indexing a bunch of different things, and I need to make sure I'm indexing them properly and using the correct things. Manual fan control operating mode. Test mode. When operating a manual thing, software controls the speed of the fans by directly programming the PWM duty cycle, which is how it should be. The operation of the fans can be monitored based on reading the temperature and tack, setting regs, or polling interrupt status registers. Polling. Set the mode into manual mode. Write 111 to bits 7 to 5 of zone mode in 5C or 5E. I would like to find that in these tables here, because I kind of already know how to use these tables. Logical device configuration and/or control registers, 30 through FF. Used to access the registers that are defined to each logical unit. Yep. So these are like the IO based things, interrupt select stuff that we looked at before. So that's where we're getting this 6.1 and 60 from. So this is base IO range for logical devices. Okay, logical device number reserved. Runtime register block. PME status. Why does PME sound familiar? I'm just going crazy, aren't I? Maybe I'm thinking PWM. I swore I saw PME somewhere. Not PWM. Oh, I'm a dumbass. Okay, serial port, config port. See description, configuration, register summary, access to the index and data ports. Okay, yeah. We're probably just going to keep scrolling up and down until we know what the hell is going on here. DMA channel select. Mode from the ECR register, FTDs. See, what I would expect is that the thermal stuff would just be sitting on a register like these logical device numbers, because we already know how to access and index these logical devices. But sadly, I have no freaking idea where the fan control stuff is. So the 3 pins, fans equipped with the tag. Okay, all the registers are reset to their default values. PWM 1 through C3 are set to fan, always on, and full, which is the mode that I want them in. Obviously, I want to be able to modify them, but at this point in time, I would love to just, if I can find the registers, it'll be easy to tweak them in the future. IO base. So those are those registers. These are the test registers, and these are all test modes. This would be really fun to reverse out what these are doing. That'd be like more hardware reversing. But sadly, I don't want to like brick these devices because I actually use these computers, so that would suck. So we will save that for another date. Configuration address byte 026. We're not using that, but that seems interesting. Oh, interesting. This allows you to change this from like 2E to something else, I'm assuming. Okay. PLL control, oscillator control, address qualification for, okay, power control, hardware revision. That's hardwired. Why can't I write that? I want to like write new lines on the chip. That'd be fun. Config control. So what are we using? We're using 7, which is the logical device index. So this is config control. So this is the config register summary. That sounds configuration registers. So this is probably similar to the device thing where we're going to send a 2 and then we're going to send something else. Configuration register summary. And let's look for that 54. Oh, what? What? Configurations register summary. Config control, device number. Okay, so that's config control. Never mind. Oh, that makes me sad. All the test things. So this kind of lays everything out. Maybe this isn't how you actually access the thermal stuff. There's gotta be a way. There's gotta be a way. Configuration mode. Config key, by writing that to the config port. So maybe I don't want it in configuration state. Maybe it doesn't have to be in config state. Maybe I'm supposed to actually be writing to 54 directly? They're defined in PME status 1. Let's find something that uses that. PME STS1. Trickle power functionality. When it's running under VTR only, PME wake ups. Okay. PME status 1. PME status 1. Alright, here we go. What's a ECAP fight? ECAP FIFO. What is this stuff? This seems interesting. This seems more hardware level. Device control register. Address offset 2. Strobe. Mode 11. The data byte written to this address is placed in FIFO. Refer to that. Refer to that. Everyone wants me referring to this. But where is it? See this for more information. Oh, I can click on something. Okay, runtime register description. PME status register. So that's set when it wakes up. Okay, and PME status. So these are located in an offset from PME block. The address programmed into the base I/O address register for logical device A. Okay, what's logical device A? What are these things? So these are like thermal registers. This is kind of what we want to get at eventually. But how do we talk with these? Like, these are all of the registers we want to write. And here's the summary of every single register. Hardware monitoring register set. These registers are accessed through an index and data registers scheme using hardware reg index and hardware reg data registers located in the runtime register block at offset 70 and 71 from the address programmed in logical device A. Okay, so I think we have to, when we were working, like right now we're working on logical device 7, and I think we have to find logical device A, runtime register block. There it is! Yes! Everything's making sense now! Ho 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 ho! So this is the device. So we want to, we're gonna delete that. So what we're gonna say is, start configuration mode. Then this is going to be address the runtime register block, runtime block device OXA. Then we are going to send the, what is the next thing we send? Did I do that backwards? I think I did. I want to do, this one is C, I think? No, it's 7. So this is 7. Then we do A. So I forget the name of this thing, so we will ignore it for now. This is, what is 7? Shit. 7777777. You then, okay, a logical device number configuration register. Write the index of the logical device number configuration register. So then we send that we want to query device A, which is the runtime register block, and they're programmed. Okay, oh shit. That was the one with the good table. No! No! We can find it. It was a big table. I'm curious what that security byte stuff is. Try and remind me if I forget about that before. I think we're actually going to get this to work. Logical device A. Where's that nice table? Here it is. So at the top of this, it says we access this by these registers are accessed through an index and data register scheme using hardware register index and hardware register data registers located in the runtime register block at offset 70 and 71 from the address programmed in logical device A. So we're now set and we're talking with logical device A. So now we want to go to offset 70 and 71, and let's just get these correct. So 70 and 71 for A. Logical device A, runtime registers. So for some reason it doesn't mention those, but I think I'm reading that correctly when it's saying runtime register block at offset 70 and 71 from the address programmed in logical device A. Is there another offset? There's an address programmed in here? Primary base IO address? Oh, so it's those things. So I think I want to read 60 and 61, and then that will give me the IO address, or the base IO address. Yeah, is that right? That doesn't sound right. Located in the runtime register block. Configuration register. These are the runtime registers. I would consider this to be... Oh, there's the PME status 1. Let's find something else that talks about device A. So, logical configuration... Where's device A? Device 4, device 5, A, device A. So, continued. So this has all this shit. And security control register. Okay, that's not quite what I want. It's located at 70 and 71, which makes sense, but let's see. Is there anything in here that we can pull that will be a constant value? Default value 0, FF, device ID. There we go. So let's try and pull one of these device IDs. So let's make a aggressive assumption saying that we're gonna write 70, write to port 70 or offset 70 in the runtime register block. We're gonna write 70 there, and then we're going to output DXAL. This is going to be the move X OX. This is going to be our index. I'm taking a shot in the dark. To me, this makes the most sense, but I might be wrong. So 3D is the device ID. And, oh, well, the issue... Let's actually do the company ID, because this is, like I said, this is a different spec. So we'll pull the company ID from there. and that's at 3E. So we're basically writing to 70, which we are assuming is the index, and then we're going to do this sequence again, but we're going to do 71, and then we're going to read from there. So we'll read in AL DX from 71, and then we'll move XOR AHH and move that into DX and out hex that. So now what we're doing is we're writing that, and what we expect is to get this company ID of 5C. So this might not work. We're taking a pretty big shot in the dark here. Nothing like guessing. Okay. Booting, 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 booting. Please work. Please work. Fuck. Work has not worked. Oh, I didn't want to close that window. That's fine, though. So basically, it seems like we do have one more level. So scheme using the index and data registers located in them in the runtime register block at offset 7071 from the address programmed in logical device A. So what is the address programmed in logical device A? So we need to find that information. Let's also see if there's anything else. Runtime register. I think, are these what we're going to be working with? What are these guys? Runtime registers. Located at address programmed from the, also referred to as the runtime register. Address programmed into the base IO address. Aha! So we do want to pull that base IO address. So we're going to pull that base IO address out, and then we're going to, I guess we're going to write to that address. What? They're located at the address programmed in the base IO address for logical device A. So we'll go find that base IO address, which will be logical device A, base IO address high and low. So we're going to want to fetch those, and we're actually just going to go back to where we were for this guy. So we're now back to where we were with the serial port data, because we're doing the same thing, but now instead of serial port we're going to do 4. So this will give us the address that now at the end of this in CX we will have the primary base IO address for the logical device A, the runtime registers. And I don't know if we actually have to do IO on that or that memory is valid. So it sounds like it's, let's see if we can find more information on this in the meantime while we wait for that to boot. So runtime register. They're located there. They're powered by VTR. Summarizes them. Okay. So register offset. So I'm curious how we actually query these, because this is a lot. Like, I highly doubt they're using this much I/O space. Runtime register POR summary. Oh, that's power on reset, the state that everything's in. Runtime register description. They're located in an offset from PME block. That is programmed into the base IO address register for logical device A. Located in an offset from PME block. So that is the address we have. So we have PME block if we pull up our video thing. So we have PME block, then we need to do register offsets on that, and I'm not sure how we query that device. Come on. So 400. So I wonder if it's IO device 400. Let's see what Windows has in the device manager. If there's like a huge block. Oh, motherboard resources. 400 to 400 BF. So maybe that is correct. Maybe that's what it actually has. PME status. Once again, let's look for some magic value here. Register offset C. Default, reserved. Was this the same table as this? This is hardware monitoring. These are accessed through hardware reg index at runtime register 70 and 71. So let's go look at 70 and 71 here. So I think these are actually 70 and 71. Perfect. Everything's starting to make more and more sense. Okay, this register is used to access the registers located in the hardware monitoring register block. The value in this register is the index, which determines the register currently accessible. Yep, that makes sense. That's typical. So what we're going to do is now that we have this value in CX, let's actually save this off, just to be careful. We're going to call this whatever this thing is called. This is the PME block. PME BLK. And this is that. We're going to move into PME block CX. This is a word. And we're going to print out that PME block there. And then what... Actually, we're not going to because we know that's working. Then we go to 70 and 71. So we're going to add 71 to that. So this code is not optimized for speed or size, so everything's going to be very verbose. So what we're going to do is we're going to do word PME block here. Then we're going to do an add on DX of 70. This is going to give us the index for the hardware register index. And then we're going to do an out DX of AL, and we'll do a move into AL of one of these hardware registers. So now we can access these hardware registers. So we should be able to hit, let's go for the company ID register. Not the device ID, but the company ID, which is 3E. And we'll output that. So we're saying we want to query that register. And then we're going to do this plus 71. And then we'll do an in on AL DX. And then we'll XOR AH, and we'll do a move DX AX and call out hex 16. Okay, so now what we're going to do is we're going to write that we want to access register 3E from the hardware monitoring register set. And then once that's been written, we're going to read the actual data that is located there. And let's see what this is. So let's reboot this box. First let's build it. Get it built. Shut it down. Bring it back up. Cookies. Okay. Boot, 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 boot. More, boot. 0. Shit. Well, that's not what we wanted. Let me think here. Using the runtime register, we write, this register is used to access the registers located in the hardware monitoring register block. Value in this register addresses, which one is available. By default, it's 0, which is VTR POR. Okay. Oh, power on reset, yeah. This is used to read-write the data in the register that's currently indexed. See hardware register index at register offset 60? But it's at 70. Yeah, that's just a fucking mistake. So that's just a problem in their writing. So I'm curious, now this could be where we're having issues of compliance between the two specs we have. So we are moving CX into PME block, then we're pulling that into DX. We're writing that, we're writing 3E there. And let's actually do an in on that same thing. So let's make sure that our write is successfully occurring and that we get 3E out of this. If we get 3E, that means hopefully it's kind of behaving as expected. Otherwise, we might need a different offset, because once again, this is a different Super I/O device than the one I actually have in my machine. So that is where it could get tricky. Hardware index. So so far it seems like this is correct, this 400, because when we looked at here, there's this huge use of I/O space, and it's declared as motherboard resources, so I'm assuming this is actually what it's used for, is these I/Os. General purpose I/Os. That's kind of cool. I didn't know these things had so many GPIOs. That'd be kind of fun to solder some wires on there and have like my own device. So that maintained 3E successfully. So let's check out these hardware things again and see if there are any other things we should try and read. Device ID, all this stuff. So we could get the temperature absolute limit. We could just try and write one of these fan things. PWM configuration. Let's see. So back to the actual work with the fan. Come on, where is it? Where's it? Here we go. Fan control. Zone 1 is remote down processor, zone 2, zone 3. So we're just going to set all 3 zones. Limited configuration registers are for these different things. So 54 through 5B. Yeah, okay. Yep. Cool. So we want to put it into manual mode. Observation of these fans can be controlled based on reading the temperature and TAC reading registers and or pulling the interrupt status things. To control the PWM outputs in manual mode. To set the mode to operate into manual mode, writes 111 to bit 7 to 5 of zone mode located in registers 5C through 5E. 5C through 5E. So these are, we want to write 111 to 7 to 5. So that's for zone, whatever those are, Xeon. Maybe that's, yeah, Xeon instead of zone. So if I put those into manual mode, then the speed of the fan is controlled by the duty cycle for that PWM output. The duty cycle must be programmed in the registers 30 through 32, which is the PWM, current PWM duty cycle. Okay? It's kind of a shot in the dark if we just start writing these things. I'm curious if there's a way that we can just force these into maximum speed mode. So let's hit one of these guys. So let's hit 5C through 5E. So here we're going to say 5C. Then we're going to write. We're going to have to read from there. And let's actually see what's in 5C. Before we do anything else, we're sending 5C, putting that in the register we want to use, then we're reading from 71 in ALDX, Zora H, move AX, DX, call out X. Okay, so let's see what this guy does. And if we can get this to come through, apparently its default setup is 6.2, and let's see what that is, 6.2. 0110 0010. So hopefully this will have some bits set. If it doesn't have bits set, if it's just 0 again, I'm going to be really worried, because that means we probably can't use this spec directly. Oh, fuck. Oh, that's really frustrating. Because we're definitely, I think we're querying the device A. We're doing that correctly. Yep. I'm getting 400 off of that. And then we're having problems. Let's see if any of these things are descriptive. So these are the things we're indexing here with 70 and 71. And we want one of these to kind of tell us what's going on. And this, we just need some sort of magic number. PME enable. Come on. Eating more cookies, sorry. We're going to try and query this PM enable 1, which seems like this is what enables the different sources here. And we know that like keyboard and mouse are enabled, so hopefully that will show us something. If that's 0, I'm going to be really confused. And well, I guess we'll keep trying more. Okay, that's D. And that would be signifying that, I think that's D is 101, or 1101. So that's basically saying hardware monitor is enabled, RI2 is disabled, RI1 is disabled, and the keyboard is disabled, or enabled. However, there's no mouse, and whatever. So I wonder what happens if I plug in a mouse into this guy, and I reboot it. Now it's a USB mouse, so if this thing is looking only for PS2 mice, then this just might not work. But I'll put a mouse in here, and a mouse plugged in will reboot this machine. And maybe instead of D, we'll end up with 1D. And if we get 1D, then that's a sign that these registers are what we expect them to be, at least for the PME enable. So maybe the 71s have changed in later revisions. But once again, if this doesn't show up as 1E, I'm not going to lose sleep over it, because it is a USB mouse, and I feel like it might just not do USB mice at this hardware level. Yes, it's still showing up as D. PME enable for this stuff. Low battery, Wacom specific stuff, Wacom keyboard. SP12 device. Did we go all the way to the top? I don't think we did. Pin status register. So I'm curious. This runtime register, PME block. So the address programmed into the base IO address. So these are definitely correct. So I think we're doing this right. Like we're getting that 400 range, but for some reason 470 doesn't seem to actually be the correct field. Hardware register index. Register is used to access the registers in the hardware monitoring register block. This value is in the value in this register is the register index, which determines the currently accessible register. I wonder if I need to enable this mode. Hardware thing is located at that. Yes, it's made read-only. No, it's not made read-only. So what I'm wondering is if maybe this table isn't accessible. Maybe it has to be in run mode to access this. What if I take it out of config mode? So we'll go back to adding 70 and then wait, what? What am I doing? PME block. Oh, I did that wrong. I was getting 8 in field 8 of this, which I don't know what that is. So what we're going to do is we're going to take it out of configuration mode after we have gotten our location for the PME block. Then what we're going to do is we are going to query in 70. Let's make a loop here and query multiple things. So let's do move the thing we want to query. Let's say BP will start at 10 because this table starts at 10. So we'll move B. Oh shit, that's not going to be. Yeah. We can't do BPL. So we'll need to do CL. Are we using CL? No, we're not. So we'll move CL into this, move ALCL, and then input from that, print it to the screen, add DI2 so we get a space, and then we'll do a compare CL to, or add CL OX1, I guess. And then we'll do compare CL to OX, let's say the end of this table, FF jump less than or equal to, or jump less than dot loop. And so that should go through all of those, and we're not smashing CL, so that should loop through. So basically, we'll dump that whole damn table. And maybe that will give us some insight, and hopefully we won't break anything by reading all those addresses. Come on. Might want to look at these high limit and low limit things, because these are always zeros and Fs, which seems to be a pretty constant dealio. FF. Shit, why did that not do more? If CL is less than that. Oh, jump less. I want to do jump below. That was a signed operation. Well, just wasting more time rebooting machines. Oh well. Yeah, means I get to eat more cookies. So it is worrying that these device IDs and company IDs are not coming through. But we did make that one change where we took the device out of config mode. So hardware monitoring register set. So let's see if there's anything else that talks about this hardware monitor. So let's see. Undefined registers, monitoring block, ADC. Okay, so that's how I do temperature, voltage, and fan speed monitoring. Hardware monitoring block is accessible via the LPC bus. Yep. Hardware monitoring fan control. Yep. Analog power dedicated to the hardware monitoring block. Hardware monitoring block. That's the interrupt output. Input. This is all hardware level stuff. SIO, Super IO device with hardware monitoring. It's powered by HVTR and is accessible via the LPC interface. This chapter offers an introduction to the Super I/O functional blocks, registers, and host interface. Details regarding the hardware monitoring block are defined in later chapters. Okay. Hardware monitoring block contains the temperature monitoring and fan control functions. Let's boot it up, and that's all F's in that table. And we're going through 10. Huh. That's worrying. Don't know why those are all F's. So if we take it out of, maybe it was that we took it out of the, what's it called? Oops, that was wrong. We want to leave it in config mode while we read that, I guess. Maybe that was the problem. So let's drop it out of config mode and boot this guy back up. And if we don't get F's, that means that we're still reading something valid, in my opinion. Because if those are F's, then that would be a sign that this is related. So if this changes and is not F's when it boots, that means there's some relation between the config key and these registers, which would be a good way of saying that we're not just reading random ass memory. There we go. Okay. 0, 1, 2, or 10, 11, 12, 13, 14, 15 hex. Is there anything at 15 hex? I'm looking for that table again. Fuck, where's that table? DLab. Come on. GPIOs. Okay. Not that. Not that. Are you kidding me? Why can't I find that table anymore? This is just not right, though. There should be a lot more going on in this hardware monitoring table. Let's read through this a little bit. See if there's anything we're missing. So there's the logical device runtime registers A, base 70 and 71, which then opens up HLM register access. So the HLM block registers access through the index and base register. So one thing we could do, it'd be kind of a really interesting concept, but we can look for endosasm on B16 super IO dot bin, and then what we can do is we can look through for the instructions that we use to work with shit, where are they? The ins on 70. What's 70? It's that trip before a halt. AA. So actually, let's look for that sequence. Basically, we want to find the B8AA00EE. B8AA00. B8AA00. Okay, I needed the... Haha! That looks relevant. Oh, look at that. Super IO. I guess IDA already recognizes this 2E thing. 2EAA. So you can see it's starting, and then it's outputting to 2E, which is the index register. It's what is it doing to this? It's outputting AL, which comes from that. So this might be like a write register function. Let's see if there are any other references to the Super I/O stuff. There looked like just a few. So there's that one. There's this one. And there's this, but that doesn't look like code. So let's find this guy. And since he is exiting with jump BP, I'm assuming this is the function. Start? Nope, it's not. Let's keep pulling stuff, I guess. No, CMC, that's not right. Shit, where's the start of this? EF. Out DL, in ALDX, move DX that. So there's a code xref here. Right, MSR. Jump will equal. Okay. So it's definitely doing Super I/O stuff here. So what we need to try and find is here it is doing more PCI stuff. What's this? It's funny how basically everything here is code. And it's 2EOC. This is still Super I/O stuff. So if we can actually find something that we want to find something that uses that 70 essentially, but the thing is, odds are nothing's going to use 70 because we've kind of come to the assumption that 70 is not correct. So you've got another function and CMOS RTC, CMOS timers. This is our entry point to the kernel, is it not? More code, more code. Return, yeah. So, question is, if we now look for Super I/O, or Super I guess, text Super I. Oh, that's going to search for quotes, isn't it? Super I/O enable register. So we're setting that. We're outputting 5 to there to enable it. Then we are input from 2F, the data port. And then it exits the configuration phase. So it seems like everything is done in the configuration phase. So it seems like we are kind of in the right area, roughly. I think this PME BLK is correct. And we can try and verify that by looking for move AX OA, maybe, out DXAL. So let's look for that. So here we go. We'll look for this instruction sequence. B8 OAOE. Yeah, I'm not surprised. What I think is actually happening is someone's going to go through and someone's going to be calling a function that handles that Super I/O stuff. So let's search for another Super I/O thing and try and find xrefs to this. It's jumped from here. And what is it doing? Load SB out 2F. It's doing a loop. So it's looping through this a lot. I don't think that's for what we want. This one does a move to E output on that, and then it exchanges AH and AL, increments DX and outputs there, and then calls this function, which then cleans it up. So this might be 60 and 61. So this is probably right to the what is this? This is right super IO index and what is it? Close. Yeah. And this is call this super IO exit config. So what's this guy do? Entry config. So that's kind of frustrating. So this is going to entry config, and then it's going to issue this takes in two parameters in AX, and it outputs the word. It outputs the word, yeah. So it outputs what is in AX. And you can see here we have in AH we've got 61, and in DL we've got BX super IO entry config. So 60, what's this guy do? Entry config, index and close, index and close. I don't know if those function descriptions are quite correct. I was comparing, looking for exit codes. Call super IO entry config. We're issuing entry config, exit config. Okay, so we're issuing 30. And what's 30 going to do? Do we use 30? No, we use 7. So what would stand out here is anything that's using 7. But then it's going on, so this is doing entry config, and that's doing and this is simply entry configuration phase. Then we do a call into this, which seems to actually write it, and this enters config and writes a byte. Okay, that's interesting. So this is super IO. Oh, here it is. Here's the 7. So in this function, what it will do is it will write the 7 and then followed by BL. So it will take in BL as the parameter of the device you want to index. So this is going to be, and then it does super IO index and close, which will basically transmit AX, as we saw here. So if we go into this guy, he's going to output AH and AL by using these exchanges. So what this is going to do, it's going to write out 7, and then it's going to write out what's specified in BLs. Let's see. So we're going to call this, this is, I don't want it repeatable, I want a single comment. I'm going to say this function takes in BL, inputs the device, what is it called? The whatever the A is sort of thing, OXA, come on, logical device. So BL specifies the logical device number, and then it also takes a, so it sets up, it says, it goes into configuration mode, then it does a, then saves AX there, enters config mode, it writes that we want to access a certain logical device, and then we call sub, this sub, we move that, we do an output of we do an output of AL, and then we input into AL. So we output AL to it, and then we read it. So this one's going to be AL is output as the, or input to this function. It is going to be the, what was it actually? Was it the value to write? Yeah, it's the value to write. So AL is the value to write at logical device. Actually, it is the, I just want to make sure I'm getting my terminology correct here, so we'll say logical device. So the logical devices have all their registers. I want to find that table, but we suck at finding that table. Oh, come on. It looks like that was, nope, that was one of them. But this is the, we're doing duty cycle and configuration registers. Here we go. Logical device summary. Then we write the config register. Register to write. So we go in here, and then we write at, we say we want to write at that config register. Is that correct? Yes. And then we input what is at that config register. So, and then AL returns the config register contents. So we're going to call this super IO query device register. So basically, it'll take in the logical device number, and it will take in the config register to write, and then, or to read, actually, and then it will return into AL the value. So this is going to be, we'll call this super IO read write reg, or write read, or query. We'll just call this query reg, because that's all it's doing. You're specifying the register, and then it's returning. So entry config, write super IO, index and close. Then we do query reg, and then we exit config, and then we return. So we can see this guy is now going to be querying device 0, and he's looking for register 30 in device 0. So device 0 is the floppy drive. So that's not what we want. Then this one is looking for 60. Oh, so now that that device is queried, they just do rapid successes after that. So we want to find other uses to this function as we go along, because this one seems to be the write index and close. There's a 60 and 61 again. We want to find someone who's using the runtime register, so A. So we want to find, because if someone's using the runtime registers, there's a good chance that they're going to be accessing some of this stuff. So these are our helper functions. What does this guy do? Write super IO index and close, write super IO index and close. So this one, oh, AHBL. Oh, that's the 7, the initial 7. Yeah, okay, 7 BL. Almost the same thing as this. Enter, isn't this the exact same function? To the byte. Push DX, enter config, push AX, write index and close, pop AX, write index and close. Oh, so this is going through if you want to write twice, essentially. So it's too deep. Interesting. So this will do, we'll call this query device register. How's that gonna work? Let's call this super IO query device register 2 for now. Yeah. So it seems like what this is doing, entering config, it's doing the same thing here where we're querying the device, and now the device is in a state where we are looking at a specified thing, and then we're going to, AX is going to specify the 2 values to write. So we're gonna, oh, so this is going to be not query device register, but this is going to be write device register. So this one's query device register, and this one's write device register, and we can put the comments, we'll steal these ones, and this is going to be logical device number in BL, that's still correct. Then the config register to write goes in AL, and then AH is going to be a config, or data to write into register. And I don't think there's any returns, we'll check on that, and then we'll also check on that AH stuff. So we're exchanging AH with AL, and then we're writing AL, so AH is actually the config register AH, and this is AL, and then we'll swap these for consistency. So config the register, that is the config register we want to write, and then we know that because AH has the config register, it's immediately swapped, and that's what's being output first, and then we exchange it back, increment DX, then we output there, and we don't return anything from this, so that's all that does. So write device register, query device register. So let's see what writes device register. Xrefs. So this one is writing. This is kind of cool. This is their interface. So this is writing to the floppy drive. It's writing to register 30, which is the fuck all I know. It is the activate, and it's writing 1. So what this is saying is activate the floppy drive. So that's what this thing is. If we make a function here, which is what's it? P. Fuck. P. We're gonna call this activate floppy drive. Floopy drive. Yes, the floopy drive. Oh, nothing but a floopy drive, yeah? Oh, shit. How many times am I going to screw this up? The floppy drive. There we go. So that's all this does, is it activates the floppy drive. So this is cool. So now we actually kind of understand what API they're using internally in their inside their stuff. So we're getting there. We're getting there. So what else is there? What's this guy do? That's PCI config shit. Let's go find who else uses write this. So and this is this an absolute call to 6A? No, it's not. This is relative. Damn it. If it were absolute, then we could find all references, even the ones that IDA hasn't disassembled. So the problem here is since we haven't disassembled every piece of code, we're not going to get all the xrefs. But we can see what this function is doing is it is querying device 0, which is the floppy drive, and then it's going to be writing to 60, which, if I remember rightly, that is the IO base, and then it's going to write 61, I'm assuming. Yeah, there it is. So this is setting up the IO base for the, let's create function here, and this is entering the config. I don't know what these things do. These looks like little helper functions, PCI config. Oh, interesting. It's pulling the 3FO, okay. So this is doing set up FDD IO base. So that's what this function's doing. Yeah, this is fucking awesome. Write device register. Next one. This one is doing, it's writing to device. What device is it writing to? We're on FDD, so it's probably more floppy drive stuff. I think what it comes down to is we haven't really discovered more code other than this isn't code. Shit. Super IO, entry config, exit config. So we need to uncover some more code. That's not code. Seems to be a lot of inline data. This might be code. Yeah, that's code. So, actually, ooh, this is, holy shit, how much code did we just uncover? A lot of code. Oh cool, this is video stuff. Oh my god. It's so beautiful. PQRT ABC. Okay. What's this? How much code did we just uncover? Holy shit on Munch. Okay, so we have a lot more code exposed now. Let's go to one of our Super IO functions. And let's go to this write device register. Oh, we haven't gotten anything more here. But since we know the input style to this function, what we can do is, let's look in xref here, and I'll see the way this worked is it built move AL 30, B001, B300. So what we can do is we can try and look for other, oh shit, we can look for other things that do the same code, but on a different device. So right now it's querying, so let's do B430, so B001 and B300, that's activating the floppy drive. Let's go find something that activates the serial port, for example. So if we go find the serial port activation, serial port is logical device 4, so we can do B304. Oh man, no one's using that code. Let's find B304 followed by a E8. So we're looking for any call that's followed by a move BL of 4. Oh, really? Oh, that's no fun. Oh, no. Shit. Somewhere, someone is accessing this. We gotta find where. Let's see, what are the other Super IOs? There's the query device register. And this is BL, once again. So it seems like we can have other stuff in the way. So what we want to find is we want to find a move BL followed by maybe a few instructions, then followed by a call to the Super IO thing. But don't really have a way of doing that. I guess I could do that in Python. I could do that in C. Or we could scroll around some more and just try and hit code on some things. And there we go. BL3. Parallel port. 30. So that's enable a parallel port. What's this one? Query device register on 3. Parallel port. Nothing. B9. What? Let's actually go above this stuff. So all this stuff is solid code. And that's definitely data. This stuff could be code. Okay, does any of this call? Let's get something. This is kind of code. I think it's code. Super IO enter config. Write device register 3, write 60. So this is actually the same thing as the floppy thing. So this is initializing the. So let's find xrefs to this now. There's going to be a shit ton. Yeah. So there's that FTD stuff. This one's C001. And what device? BL. Where's BL set? BX 6A. I don't think that's correct. So it's querying F8. 7474. Okay, EF. Okay, let's start from the top of this thing if there's a top. Super IO entry config. I think this is the start of the function. Or push 80, push F. Your function. Boop. And so super IO entry config. This is going to set up the base address of the device 3, the parallel port. Then we're going to do a write index and close on FO after querying 7070. Not quite what we want yet. 3BC. I think 3BC is parallel, isn't it? That sounds kind of familiar. 3BC, yeah. So this is definitely parallel port stuff. So we'll call this setup parallel port. Okay, got more code here. This is querying device 3. So this is more parallel port. This is querying registers. This is querying the parallel port. And we'll make function query parallel port. What's this guy? There we go. There's a 4. So this is we're gonna see like a 3. This is fuck serial port, right? 4. Device 4. Yeah. So this is we'll call this function setup serial port. And we come through. This one's probably going to be more serial port shit. This is going to be BL5. This is setup serial port 2. Setup serial port 2. What's this guy? So this is 5. This is query serial port 2. This one is this one's query serial port, and then we go right into, okay, so there's some more stuff, then the FDD stuff. Okay, so we've gone through the parallel port and 2 serial ports. So where's my fucking, oh, this is an interrupt handler here. So that's interesting. Don't know what that interrupt handler is for, but there is one. What's this guy? Is this code? Yes, it is. But doesn't seem relevant quite yet. Code. Make some fucking code. It doesn't look very codey. That's fine. This is a nice block of code. So we're looking for more things that are doing super IO work, essentially. So right now we've uncovered serial, parallel, and floppy controller, but we haven't covered that device A, which is the configuration registers, the runtime registers. So we want to get access to those runtime registers. Man, I just been doing fucking work. So, runtime registers. Okay, there we go. Yep. That's probably data. Okay. Crazy how much fucking code is in this BIOS. Okay. So it seems like all the Super I/O stuff is kind of in one location. We've defined everything that accesses that. We've defined everything that... no, we haven't. This is doing 5. Oh, this is function. Now look at this. What's this? This is querying parallel ports. So this is query... FDD, actually. And so, what else? This hasn't been defined. This is on BL3, which is the device number. This is parallel ports. Query parallel port again? What? I thought we already had that. That's fine. Basically, I'm naming things that aren't referring. So this is accessing fuck off, and this is accessing 3, so this is serial port, this is parallel ports, more stuff. So sadly these names are going downhill, but I just want to be able to look down the sides of these XREFs and say whether or not we have identified everything that uses these. And it looks like we definitely know who's calling all these functions. So let's hope that somewhere we can find... I don't think that's code there. This looks like code. This is definitely code. This is... okay. Haven't gained any Super I/O stuff yet. CMOS. And come on. We just need to find something that accesses that Super I/O stuff. And what would be interesting, and maybe it's something that we will make if we don't get there in the next few minutes, is make a little Python program. So the reason why I'm trying to go through and find and identify actual code in this BIOS is because that's IDA will tell me if it's calling the Super I/O function, and anything that's calling the Super I/O function will be calling it relative. So it's important for me to have all this code defined, because then it will add an XREF to that code. But shit, now this is like boatload of code. That's not code. This is code. This is probably code. This is code. This is code. Pick. Setting up the pick. Setting up more shit. So we definitely identified a bunch of Super I/O functions. But the question is, do they have redundant Super I/O functions? Like, is there... because these functions actually are using the stack and calling and returning things. So what I think is happening is that there's probably other Super I/O code that's actually being run before the system is fully running. Because you can't access RAM and you can't use the stack this early in the process. As early in the process as a lot of stuff. So we've defined more code. Come on, IDA, just fucking like define everything. Oops, shit. I'm curious what would happen if I did an analyze area right now, if that would get me anything more. Let's do an analyze. Let's go into IDC. Analyze area. Let's do 0 to -1. So let's analyze everything, and it went through, and it doesn't seem like it found anything new. So Super I/O stuff. Let's go into one of these guys, see if anything has showed up for an XREF. Nope. So once again, I think we're going to be back to the ground steps of looking for this BA2EOEE, which is basically the register for Super I/O, and that is, okay, so we have these guys. Oops. Let's go here, and here, and then we're here. So this is doing Super I/O work in an environment where you don't have stack. So what you can see is we're doing jump BP here, whereas in these other functions, these look like, I mean, they look like just normal C stuff. But if we look at this one's doing a jump BP, you'll find there's no returns around here because you can't return yet. So this might actually be the same Super I/O code, but this happens to be written at a level. This could be the same Super I/O code, but it's written at a level before you have execution, before you have memory access. So when you're doing BIOS dev, you don't actually have memory when you boot up. You have to do everything solely out of registers, or use cache, or use read-only memory to get access to the memory you're interested in. So what you can see is that obviously this is Super I/O stuff. So they have two implementation of Super I/O. It looks like we pretty much fully exhausted the reversing on the easy side of things. So now we got to check this one out. So here we can see this is initializing, entering configuration phase. This one is leaving the configuration phase. And I think that there's going to be a good chance that that a lot of these functions are going to have the same C code that implemented them, but it's just a different compiler output. So what we might actually find that a lot of things are practically the same. We might find that a lot of the things are the same in this code as we saw in the other code. So there's this loop, which is a little bit confusing here. So loop is a very shitty instruction. It's a very slow instruction, but what it does is it decrements CL, or CX actually, until it gets to 0, and it will keep looping until it gets to 0. It's a very lightweight instruction in terms of encoding. It's cheap, but it's very slow, as it's been deprecated in recent processors. It's still present, but it has been put at the very, very back of the CPU, so it's not an efficient function. So if you ever see someone using loop as an assembly instruction and it's not for shellcode reasons, yell at them, because it's slow. You're better off with a decrement and a jump, or a sub immediate 1 and a jump. Nevertheless, I'm just putting off the inevitable of trying to figure out what the fuck this thing's doing. So here he's going to initialize, and then he's going to write AL to the configuration thing. Then it's going to increment DX, and then it's going to write that again. It's going to loop for every iteration. So what I think this is going to do, what this function does is it takes in two parameters. SI is a pointer to a buffer of ins and outs to perform. So what it's going to do is it's going to pull SI, and then it's going to output AL, and then it's going to output AH in that order. Yes, that's correct. And then it's going to loop around for every device you specify. So basically, the input to this function is SI is a pointer to a vector of operations to perform, and CX is going to be number of operations to perform. And so we're going to call this perform super IO. I want to have some prefix to specify that it's pre-reg. So let's do no mem. Let's do no mem super IO perform vector. And what I think you're going to find here is that things are probably going to call this, and they're going to pass in a vector in SI, which is going to be the parameters from, or they're going to be some random shit in ROM. So it's basically going to say, hey, run these instructions out of ROM. So it's probably going to be a huge chain. So what you see is it initializes Super IO, it tears down Super IO, and it's just going to probably execute boatloads of operations on Super IO. So if we look at this, we can find who references it. Actually, first I want to look at anyone else who does this 2E out. And you can see there's someone else who does this here. This is in a... this one is enabling it, disabling it at the end, and doing the same loop as well. But this one's pulling F as CX. So here it is. Here's exactly what I was talking about. So this is saying execute 15 of these ins and outs. So if we go here, that looks like code. Move SI. Okay, we need to figure out what segmentation is. It's doing CS SI, so code segment. Yeah, that's correct. So it's going to be going to this. So this is data. And what we should find is we will want we want 15 words here. So how many do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And this is probably the start of this function. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And what this is going to be doing is AL is going to be output, and then AL is going to be output to the index register, and then AH is going to be output to the data register. And then it's going to loop around. And this is a hard-coded function, so this is going to be, we're going to call this, it's a function starting here, and we're going to call this super IO, or no mem super IO perform static this. So what this is this function is similar to our perform vector, but instead of, this one takes an input in SI and in CX, but this one directly has CX and SI hard-coded. They will never change. So this does the same exact thing as the other function, and what you'll see is this will end up executing. It will issue, so it will issue 2, and so that will, I don't know what 2 is, so we can go to our table here. It'll do config control, so it'll send, it will write 0 to config control. So it'll do config control, it will write 0. So it zeroes this config control out. Then it will write 7, to 7 it will write 0, so it will select the floppy drive. And then it's going to write, to 60 it's going to write 3FO. Oh my god, this is so cool! So this is 3FO. So you can see right here, it zeroes out the config control. Then it zeroes out, then it selects device 0, which is the floppy drive, and then it sets the ports to be 3FO on the floppy drive. So if we look, if we just Google, oh my god, this is awesome! 3FO and IO. What will come up? If my Google works, look at this, 3FO, 3FO. What is that 3FO? The floppy disk controller, of course! This is awesome! So, I don't know if this is common in BIOSes, but this is what it's doing. And then it's going to issue, then it's going to write 6 to 70. I can't remember what 70 is, but 70 is the, that's not right because we're in a IO device. For the, oh, it is correct. It is the primary interrupt. So we're setting up 6 to be the interrupt to use for the floppy controller. Then we're passing in to use in 74. We're doing DMA channel select to 2, and you can see that's the default here. So it's kind of doing a reset on everything. FOOE, so that's writing to FO FDD mode register, F4, blah blah blah. F4, yep, F508. So that's FDD1, I guess. And then it goes to 3001, which is activating. So this says now activate the drive. And then it seems to go on to the next device, maybe, where it's going to 8. Oh, that's reserved. So I don't know how that works now that it's doing 7. We're definitely on the right page. Getting so excited about this. I've never done BIOS reversing, so it's very, very new to me. Oh, 7 is the keyboard. Yeah. And then it's doing 480, so if I search for OX480 I/O port, what will we get? OX... that's not giving us much. I don't know what 480 is, but it's setting 480, 480 on that I/O port, and then it's activating that device. So I'm assuming this is the keyboard activation procedure. So by doing 7, I see how it works. Okay, so by issuing a number under 30, not issuing 30 and then issuing a number under 30, it is by issuing a number under 30, it's going back to the device select instead of using these index registers. So it's selecting the 8th device. Oh, never mind. It isn't selecting the keyboard, it's selecting 8th device, which is this magical hidden device. It is a reserved config. Now, keep in mind, it's probably not reserved for the actual spec, but since we do not have access to the spec, we have access to a spec that's similar, we're kind of have to just go with this. So that's activating that with 480 as the entry point, or the I/O point on there. So I think what we'll find is if we search again for this, we'll probably find multiple instances of this same code procedure. Here we have a loop again, although this one is not constant, so this one is doing a loop. That's code. So this looks to be the same as perform vector, so I don't know how this is different. So we're going to open up another IDA view here, and we're going to go, let's find Win View, Open Subviews, Disassembly. Let's pop this over here. Oops. Come on. This guy. Grab him. Pop him here. And IDA View B, we're going to go to, in this window, let's go to the Perform Vector. And sadly, I think I lost my place. So let's go to Perform Vector on this side too. And so if we go to the next one, this is the static one, and then here's this one. And how is he different? 2E55, OutAL, SI, exchange, increment, loop. This is exactly the same. I see no differences here. So this is just another implementation of this, and it's probably due to some restrictions, but we know how that works. We're going to copy this comment because that is a useful comment to have. And then we'll go look for the next reference. Here's another one, and this one is, where's it entering configuration? I think we have some alignment problems on our instructions. There's our push A. Oh shit. What did I do? Okay, we'll go back to this one. We'll go a few ahead, and now this is where we are. So there's this push A here. Okay. I'm not quite sure. So this one's moving CX9, SI, this. Okay, so we have some problem here. This 2E, we want BA2E. This is where that starts. And then this needs to be data. This needs to be... This is actually the start of the function. So this is another hard-coded one, which is exactly what we want to see, because these guys are really easy to work with. Let's see, if we go into, so this is another static one, and it's ending at the jump BP, of course, and so we're going to call this, we're going to stick to this same naming convention. So we're going to pull this name here, and 1, 2, 3, 4, this is now FF54. So this is now going to do 9 at FF54, and let's figure out what these guys are. So this is DD 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And let's put a name on this one, and we're going to call this FF54 static ops, just so we have that name there. And what we can see here, we're going to be executing 2.4. Oh my god, there's the dreaded OA. That's what we've been looking for this whole time. So here we have, first of all, let's not get ahead of ourselves. Let's keep ourselves on our toes. We're going to go into 2.4. So this is OSC, and it's going to set that to 4.4, which is exactly what it's initializing to. Then we're going to select the A device, and we're going to set 400. So, like we saw before, 400 was the base of the A device. That is the, fuck. I forget the names of all of these things. But, basically, the A device is what we've been querying, and we pull that port and we get 400 out of it. And here we see it statically being set up to 400. Then it's setting the FO on that port. So device A, FO, is setting clock I32 to 2. Oh, shit. And then it's setting it active. So I think that's definitely confirmation that this runtime registers is what we were working with, although it's... And the fact that it hit FO, but it set it to 2. Let's look around for anything that has 2 as the default for FO. And the reason is, we don't necessarily know if A corresponds with the runtime registers. It probably does. But we just want to be extra cautious that we don't make any nasty assumptions. So it doesn't look like anything defaults to 2 on F0. So I think it's safe to say that that A device, logical device A, is probably the runtime registers on this BIOS, or on this chipset as well. So then what else does it do? Then it sets that as active, then it queries the 7th device, which is the keyboard. It sets F0 to 0, which is K reset, and A20, gate A20 select, and then it sets up that device. So basically this initializes the runtime registers and also sets up the keyboard. So let's actually just call it that. So init nomem super IO init runtime regs and keyword. That's a huge function, but it's nice to be descriptive. I'm gonna move this hex window back up to where it normally is, and we're back kind of in our normal mode. And let's see if we can find anyone that references this. So let's look for this. FF66 at 223, 2230, and this is doing a push. That's just that instruction, actually. These are all instructions that are doing pushes. E866FF, so here we have a call to, that is a call relative. 8846FF, once again, no dice. Basically, I want to see anyone who actually is using this, and I guess it's kind of going to be a bitch to figure that out. Let's textually look for that string. FF66, so that's in BIOS E. This is FF66, oops. I'm so used to hitting search binary. So there's FF66 on BIOS F, a bunch of those, of course. Then this one is BIOS Flash. FF66A7 code. Let's get that as that. FF66. I don't think this is code here. None of this does not look code-like. So we'll continue looking. I think we're at the point where this is all data. So that's a little bit frustrating. So it looks like we are finding where it's setting that config A device, the runtime regs. So this is definitely where runtime regs is being set up, which is neat. Then I'm going to want to find, now I want to find something that uses runtime regs for the, so something clock I32. I want to see, because that was getting set to 2, so clock I32. Pins on PME wake up. That is this bit is located at 0 in this register is powered by VTR. Okay. The SPEM SE enable bit in config is wake on specific mouse click feature. This bit is used to turn it on and off. I'm not sure which one that is. Clock I32, here it is. So bit 0, bit 1 is what we're setting. So we're setting key enable. This bit is used to turn on the logic for wake on specific key feature on and off. So basically, oh, this is actually turning it off. So this is turning wake on specific key off. That's kind of interesting. Okay. So that makes sense. So I think we have definite confirmation that logical device A is the device we want to be querying. And it's also, just by reversing this, we know that we want to be in this config mode practically at all times. So we set config mode, we index that port. Just for simplicity's sake, I'm actually going to hard code that register now. I'm going to call this the runtime regs IO port, and we're going to call this 400. And all that means is that we're going to be able to basically throw this information away. I know it's, and I'm actually going to save this somewhere just in case we want it. But I'm just going to throw it at the end of the file. We want to start config. Do we want to index? Oh, now I'm just confusing myself. But we're just going to use that down here. We're not actually going to save these things off. Operation complete. And here, yet another operation complete. And I think we actually can just issue the 60. We don't actually need to re-index that, as we've seen before, so we can get rid of that. According to the BIOS code, that's how the BIOS has been doing this. Then what I can do is, here I'm going through that table. So I have the IO port, so we're going to do a move DX 470. Actually, we'll do this plus OX70. And that's, once again, we're kind of back in the weeds of that really dense table. Let's see if we can find that table again. I think it's right here, actually. So 70 is the, that's not right. Register summary. Wait, why are we using 70? We have the I/O port. Oh, this is the hardware monitoring. Okay, yeah. Then there's that other table. So first of all, let's look for the clock I32 device A. FTC on PP. Yup. So let's try and find that other dense table. There's one. This is, once again, that's the hardware table. Unless all the dense tables were the hardware ones. I can't remember at this point. But we were referencing 70, offset 70 to clear that register. And just want to make sure. I was hoping that I'd just be wrong. And so 70H. So there's the HWX interface, base plus 70H. So that's the index, and we are basically moving CL into that index, which is going to start out at 10, outputting that to there. Then we're going to be doing another operation where we're going to work on this plus 71, and then we're going to input from there. So that's input our byte, which is our data, and then we're going to output that to the screen. Of course, out hex 16. Let's make an out hex 8 because we're kind of dealing with a lot of 8-bit things right now. So we're going to do out hex 8. We're going to call this rotate left by 4. That's the same, but 2. And this is going to be DL, and this is going to be DL. This is going to be AL. We no longer. Oh, we still need that. And do we do anything on DX anymore? No, we do not. So this should now work. So now instead of doing out hex 16, we'll do out hex 8. Don't need to XOR that anymore. We'll just do move DL AL, and then we'll out hex 8 on that, put a space after it. Then we'll add CL1, compare CL to FF. If it's below that, we'll continue to loop, otherwise we'll break. So this is the same thing as we're doing before that we have up here. I want to run it again just in case any of these code modifications somehow have changed anything. I'm kind of just grasping at straws here. I really just want it to work because this is confusing. Or maybe it is working. Maybe I'm expecting to see more non-zero data, and there's really only one non-zero data, or maybe I have to enable something. So let's see. Oh, someone posted something in Poning about the. Oh, this is when the rocket exploded. Oh my God, get wrecked. Okay. Okay, so shit. So now it's all 9s. Why is this all 9s? Add CL1. Now I think we're just doing something wrong, which is good. I like when we do something wrong, because that means we're probably thinking in the right direction. We're just doing in the wrong direction. So out hex 8, this should work. Rotate left by 4. That's fine. Xlat B, that's still fine. Still using the same lookup table. And I'm not smashing DL, and I'm not smashing anything else, so that's fine. So here we're doing add DX 70, move AL CL. So we need to make sure we're preserving CL, and CL seems fine. So why is everything 9 in this table? I wonder if I need a timing loop, so let's do a delay here. So we'll do a dec BP jump not 0 short dot BP, and we'll do move BP OXFFFF. So that's going to be a tiny little delay loop that will just oops. So that's just going to spin around. What it could be is that I'm writing that address. I'm writing the register I want to query to the regs IO port plus 70, and then I'm reading in directly afterwards. So maybe it wants a little bit of delay for that port to be recognized. So we'll see if that works. Otherwise, I also want to make sure my screen gets aligned. So right now I'm outputting. There are 80 characters on the screen. I'm outputting at 2 bytes per character. So let's just, if we were to, since we're outputting 3, I need to add another space, and this will look a lot cleaner, but we're still in problems. So we're going to do add di4 just to clean up the space. And here, I'm curious why we're getting these 9s coming through. Runtime regs IO ports. Oh, we're doing add dx. Oops. Big no-no there. Move dx. Alright, now everything makes sense. So I'll reboot this machine yet again. Got it built, shipped out, so move DX, that port, move ALCL, then we output AL, then here we do the same thing, move DX, in AL from DX, output that, add 4 to the screen, then add 1, make sure we're below that threshold and loop around. So we will print out the first 255 bytes from this state. And we see that 9 there, and then it's at 0, 1, 2, 3, or 10, 11, 12, 13, 14, 15. So that's being printed out at 15, which is not a valid hardware monitoring register. So I'm trying to think. Either this has relocated and is in a different location, and we need to figure out what that offset is for more BIOS reversing, or I'm trying to think what else could be the problem. We are writing that at 70, and that's exactly what it wants us to be doing. If we do, I want to find that hardware stuff again. Where was it? HOM interface. So logic device A0 70. So that's the index, that's the data. So it's just a windowing thing that's kind of common. The HOM block is powered by standby power, HVTR, to retain the register settings during a main power sleep cycle. The HOM block does not operate when VCC is 0 and HVTR is on. In this case, the hardware monitoring logic will be held in reset and no monitoring or fan control will be provided. Following a VCC POR, the hardware monitoring logic will begin to operate based on programmed parameters and limits. The fan tachometer input pins are protected against floating inputs, and the PWM output pins are held low when VCC is 0. Okay, resetting hardware monitor block. There we go. Power on reset. All the registers in the hardware monitor block, except for the reading registers, reset to a default value when VTR power is applied to the block. The default states of the register is shown in the register summary table located in PME status 1. The default state of reading registers are not shown because these registers have indeterminate power on values. That's kind of cool. Use that for, I wonder if you could get some funny information out of that. We want to look for PME status 1 and see where this is used. So the limited configuration registers are defined in PME status 1. See PME status 1 for more details. Yup. See PME status 1. Okay. Offset hex in the runtime register summary. So these are the runtime registers, and PME status 1. What I'm thinking is that we are enabling the runtime register, and the BIOS is enabling that for us. But we might have to enable some more fancy stuff to get access to these HOM index registers and data registers. So we're going to keep searching around. So PME status 1, there we go. That's at offset 4. It starts out as 0. And PME wake status register. This register indicates the states of individual PME wake sources, independent of the PME. If the wake source has been asserted on a wake event, the associated PME wake status bit will be set to 1. If enabled, any set bit in this register asserts the IO PME pin. So we can see the hardware monitor here. But this is only a status thing. This, as you can see, it's a read, write, clear. So if you write anything to it, all it will do is 0 it out. So you cannot actually change this. So this is not actually something that will change settings. So the default state is shown in a summary table. Okay. Usually the first action after power up is to write limits into the limit registers. VCC power on resets. The power good PS signal is used by the hardware monitoring block to determine when a VCC power on reset has occurred. The power good signal indicates that the VCC power supply is within operation range and the crystal is valid. Throughout the description, blah blah blah, VCC POR and power good are used interchangeably since the power good is used to generate a VCC POR. Okay. So all the HOM registers will retain their value through a sleep cycle unless specified. If a VCC POR is preceded by a VTR POR, the registers will be reset to their default values. So PME status 1 for a list of the things. So these are the fields in the hardware set that will be zeroed out. This is of the hardware monitoring block, though. Soft reset, initialization. Setting bit 1 of the configuration register, 7F, performs a soft reset on all hardware monitoring registers except for reading registers. This bit is self-clearing. So if we go into the configuration register 7F, is that correct? Those are the runtime registers of the configuration register. Which one's the configuration register? Is that part of these guys here? Logical device A. I don't think so. So I think that's part of the hardware blocks. And where's that table again? So if we go to FF, that's the test register. No, 7F. That's what we're looking for. 7F, configuration init. Yeah, so I still need to have access to that thing. And here you can see these test registers are set to 9 for a lot of these. And that's kind of interesting. That kind of trips some bells. But let's see, soft reset. I would say we should do a soft reset, but the thing is, we don't think we're accessing this field correctly, so we don't really know unless we do a soft reset. Like let's actually hit that. Let's do a soft reset on this guy. So we don't need this loop anymore because this is clearly not giving us any information we don't already have. So we're going to output to 70 to say we want to write to register 7F. And then what we want to do is we want to input from that, and then we're going to OR AL with OX80, so that's will set the 7th guy, and then we'll do an output of DX on, so move BL AL, and then here we'll do an output AL, but we'll have to do move AL BL. So here we say we want to query 7F, we input the data at 7F, we set that top bit, then we save that value. Once again, we query it. Actually, we won't need to do that again. We can simply just dump that out. So input, and that actually is the same as well. So we will just do that. Very simple. I'm actually going to copy this, and then I'm going to go back, because what's the point of resetting if we can't see what the output is? So I guess I do want this table. And that's the latest iteration. So here we're going to supply that reset. So we're going to hit that with a reset, and then let's see if anything shows up in a way that we're interested. So power this guy down, power him up. So issue a reset, and set that top bit, then send it back out to the device, and that should give it a reset. And what would be cool is if the fans spun up here, because apparently the fans start off in a initially they start off in a fully on state, so it would be cool if that's how it works. It's not, and that 9 is still set in that one location, but that's it. Okay. So I'm just afraid that that 70 offset that we're using is not valid on our version of the device. And let's see, clocks. Let's make sure there's nothing else we have to enable. The device monitoring function is started by writing a 1 to the start bit in the ready lock start register. Yeah, once again, we don't have access to that. Monitoring modes, cycle monitoring, interrupt status. Hardware monitor block has 2 primary ISRs. So those two of course, and sys events. Okay, interrupt enable bits. We don't want interrupts enabled. So these have these guys that come through here. Temp voltage enable, interrupt enable, and HLM interrupt. So that's how the interrupt controller works. Diode fault, interrupt signal, interrupt pin, interrupt of a PME event, interrupt as an SMI event. That's kind of cool. I wonder if I could find a bug in the SMI handler and then force an SMI event. That'd be kind of cool. And then I get like SMI privesc. Interrupt event on serial. Low power mode. When the start bit, once again, don't access that. Temperature measurement. Data temp. Like, look at all this stuff I can get access to. But I don't have it. Following a VTR power on resets. Steps must be taken. Set limits and parameters. Set all this shit. But, once again, we don't have access to any of this, so it doesn't matter. Fan speed control. Manual fan speed control. Need a way to actually set that, find that correct field. And calculate the duty cycle, yup. Force spin up. VTR. So I don't quite know how... It seems like this device is getting properly enabled, but it's not at offset 70 as we're told here, HLE reg index. So, the issue is something has to access these fields. So let's look for something that might be touching these guys. So we could start looking for like 470 if someone hard coded the 470, because that's what we're accessing here is 470. So someone might have already hard coded that, so we can look for that. 7004. And that is not right. This is moving 470 to that. Then it's output. Look at this. Here it's doing 470. So this looks like it could be the potential for the fan speed stuff. It's the same loop shit we saw before. So SI, it's going to output to there. Then it's going to increment DX. And then it's going to output. So it's doing what we're doing here. We're outputting 470. And then we're outputting to 471. We are writing something else. So this loop occurs F times and CBA8. So we can see this guy. D, 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 D. How many times did I say that occurs? Let me see. Oh, shit. I lost my place. Oh, God. Not there. 470. Here we go. So I'm going to quickly... This is a perform vector. And here we go on 470. We loop here. And we're going operating on this. We're going to call this an offset to... oops. Undo. No. I don't want that as an offset. I want... Oh, I do want that as an offset. And I want to go here. And I want to... This is where it is. Oh, shit. I went too far yet again. Here we go. Unknown A8. So this is going to be our init 470 sequence. And there are F entries in it. So 1, 2, 3, 4, 5, 6, 7, 8, 9. A, B, C, D, E, F. 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Why is that a byte? Word. 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. That's the end of the table. This is probably code. Does not seem to be. Oh, yes. Yes, it is. Move DIBP. So this is the init 470 sequence. So it's going to be blasting these out. So it's going to send out, first it sends out 0, 0, and then it sends out 0, 4. So we are at 470, and what it sends out is 0, 0. So it's saying index 0 and send out 4. Then it's saying 1, 4, 2, 5, 3, 5, 4, 5, 6, 8, 4, 7, 8, 4, OD. And here's the 1509. So that's where we're getting that 9 from, 5 in, because we were starting at 10. So if we actually drop this down and we start at 0 and go to F and we do that full sweep, what we'll find is that if we reboot this bitch, start them up. And the issue is none of these things are documented on our guy. Nothing below 10 is documented. So I'm curious if there's a huge difference in this table. Or maybe 70 is just coincidentally also used for another address. But this boots up and we'll see that sequence right here. So here it is, 4, 4, 4, 5, 5, 5, 0. Oh yeah, because this goes to 6, there's no 5. 8, 4, 8, 4, OD, 9, 1. So exactly what the BIOS is setting up for us, which is kind of cool. But the only thing it's setting is 15 to 09. And 15 is not defined under this table. So question is, what the hell is going on here? So here we're doing an operation on SI of, we're doing 26 operations, and we're going to perform those vectors. So here we have 26 dd, and let's actually just try and do this in bulk here. Array of, how many did I say? 26. So an array of 26 words we need to define here. So this is an array of 26 hex, 38 elements and items on a line. Let's do one item on a line, element width, print width, 2, okay, whatever, yeah. Oh, shite. So this is going to be, I was using the, let's actually convert this to a little bit different thing then. Array, 38, let's print 2 items per line, but let's do one width. Oops. We want this to be hex, and we want this to be, we want these to be bytes. And then we can define an array on this guy that is, I guess, 76 in length, yeah, and 2 per. Okay. Now we got this guy. So what we're sending out is we're sending out 2, 0. Then we're sending out 7, 0, which will be querying the floppy. Then it's sending 3FO, and then it's setting 70 and 74 still on the floppy. Then we go 30, we set, this is for the parallel port. Then we set up the serial port A. Then we set up serial port B. And then here we go back to floppy. What? Duplicate 2. Why is it doing that? Is that saying 2 is there 7 times? No. 270? 2 dupe 7. Why is that there? What did I just do? What did I just do? I broke everything. Everything's ruined. We're just gonna do this. Fucking Ida. How big was this table supposed to be? 2.6 in length. So 26 hex plus CBOC goes to CB32. This is the end of the table. So 32 is the last valid one, right? Is that correct? Nope, there's another, want to add, that's 26 again. It's actually at 58, because the entries are 2 in size. So CB58, this is the, it'll probably line up where there's code. 58 right there. So this is end of table. And this one, kill that name. So, this is writing all these different sequences. So we set up parallel 1, or serial 1, serial 2, 30. Oh, we disabled that device? Oh, wait. No, I'm throwing myself off. 30 is... okay, so then we have 707. Does anything operate on A here? Nothing does. So nothing's doing fan work here. And then we go through and we then also call this, and we pass in SI and CX, and then we jump if CX is 0, which CX will never be 0, because we just set CX. That's very strange. Then we do, we output, okay, we move DX, we move 0 extended what was in SI, and SI is right here. And let's pull this to the side. Let's go right to where SI is. And SI is, you gotta be shitting me. Why are these linked? Don't link right now. Init 470 sequence. So this is going to so this is going to go through and output byte by byte. But it's gonna add 400 to DX. Oh. So we're going to be indexing off of 400 the next bunch of commands. So let me see. So basically we're pulling in the field we want to write to at 400. So 400 is that is what this points to. And then we're basically issuing a bunch of different commands. We're going to loop around, and we're just going to continuously issue commands to those ports. So what we're going to go to index 24 and write 8C there. Then we're going to go to 25 and write 5 there. And then we're going to go to 26 and write 5 there. So on and so forth. So what we'll find is if we go into this table, we'll see what it's writing to 2.4, and we'll see if these match up. So now we're in the table, we're questioning whether or not it's the same. So here it's writing into 2.4. So 2.4 is a GPIO. So it's writing 8C there. So GPIO, I would say it's weird that it would be initializing GPIs to different values. So that already throws me off a lot. In terms of this stuff is not what we're expecting. 2791. Like, why is it writing this arbitrary stuff to these things, essentially? And here it's writing to 2.8, which is read-only, which is impossible. So these tables have to be different. So basically, it's writing the runtime register. It's writing to the runtime register table, if I'm not mistaken. Let me make sure it's not writing that the 470 is. So here it's doing some weirdness. 29, 2A, 2C, 2D, 2F, 30, 31, 32, 33, 34, 35, 6, 39, 33A, 3B, C, D, E, F, all the way through to whatever. Let's find the end of this table. So it's going to do a 28 hex entry write on this, and that's times 2 plus this. So it ends at B8. So this is actually the entirety that it's going to be writing, is from 58 to B8. It's not actually going to write B8. That's going to be one before the last. So let's see. It's going to write 04 to 0. It's going to write 04 to 1, and we don't even have a 1 here. And to 2, it's going to write 5. And that makes no sense. Okay. So it's going to be pulling this value from, we're loading up SI, we're loading up CX, we're doing a jump CX if CX is 0, which it can't be because we just set it. Then we're doing a move ZX, we're dereffing from this 58. And we're getting 24. We're then adding 400 to that, so now we're looking at 424, which is this structure. And then we are writing values to it, 8C, 05, things like that. So what we can try and do is we can try and figure out if anything here takes 8C. So let's look for another table that's doing runtime register, and runtime register summary, and this is reserved needs return 0. So offset the power on reset state. So we're looking for 8C. So what I'm trying to do is I'm trying to find if these things line up with anything in this table. 8C, here we go. 2C. Then it's going to write a 5 somewhere. So that 8C might actually be what that's supposed to be writing there. Let's see if there's anything 05. Here's an 05. Then are there other 05s anywhere? Lots of 1s. So, what this wants is it wants the HOEM index and data to be set to 0. Does this set... We think that the index and data are at 70 and 71. But at the same time, we don't have any confirmation that that's actually correct. And none of this is writing to 71. So the only things it's zeroing out are 16, 19. Does it zero any two things out in sequence? Out ALDX, add SI2. So that's where we could start to see maybe if there's... Let's see if there's 91 in here. Zeros. 91 only is going to have 2-bit set, so that might actually just be one of the... yeah, it doesn't look like 91 is in here. Let's see any other unique ones. 05, 91, OC. I don't remember seeing an OC. 84, 91, 8C, 84, 5, 9, 84, 5, 0, 0, 88, 8A, 84, FD. This is really tough. So we know, one thing that's kind of frustrating is that we are doing a 470 operation here. We're doing this in 470 sequence, and we're doing F of these, and this is at, yeah, it's sending 0, 0, yeah, so this is doing 0, 0, 04, 4, 5, 5, 5. That doesn't look familiar anywhere, does it? 91, 84s, ODs. But the thing is, the fact that it's going into this 470 sequence specifically, and it's going to 470, it's writing that window, and then it's incrementing DX, and then it's writing there again. And let's see if anywhere else does a windowing behavior. If somewhere else, so this is kind of the windowing behavior we were looking for, and it happens to be at 470, which is exactly what our code says, which is a little bit frustrating, or what our specification says. But we're just not seeing what we're expecting. So if we go and look for other things, so here we do a 422, and according to our stuff, which I think we can safely say is just completely wrong now, that's UART3 FIFO control shadow. Ends it with 4, outputs it, moves AL, that doesn't seem right. Here we do a 480, we move AL 40, we do an output of that, then we do move DX 481, then we do move AL 4, so that could be our window. So 480, we're doing 40. So let's say our windows, let's say this structure is the same. So this is saying it's writing at 40, it's writing ready lock start, which happens to be exactly the first thing that would make sense to set this ready lock start, and it is setting it to 4, which would put it in a state of 0, 1, or 1, 2, 4, which would put it into a ready state, but not into a start state. Then it's going to issue 33, which is reserved. It's going to then send out an F on that. Then we're going to go to FF on 480. And that's a test register. And then we'll output 0 to the test register. That could be interesting. That could be interesting. Let's dump out 480. So right now we're doing 470. So let's do 480. Let's actually also send that reset message. No, we don't want to, just in case that screws something. So now we're going to dump out at 80. So basically the BIOS has code that does the same, it does that windowing, the register windowing, by it's writing the 480, a field, and then it's writing something to that field. So basically we're definitely in the space where it's initializing all this stuff. Sorry, a little bit distracted right now. Okay. Let's see, has it booted yet? Here we go. So this is what is in here. Now this looks a little bit more proper. So here's 20. So at 20, let's start going down the list and see if any of these make sense. So 20 is the 2.5 volt rail. What's 5C? 92. So this is, I'm not sure what these things are. So 20, 21 is the 1.5, then we got a 22, which is VCC, 5 volt, 12 volt. Then we have a diode, and apparently the degree readings are supposed to be literal. So if I look at 17, 23 actually sounds correct, 23 Celsius. And then we can do 7, 4F, 660F. Then we have a bunch of Fs. Then we have, I'm just kind of looking for these 8C, 5C. Do we see that anywhere? I do not see that. But this looks like this might be where we want to be. Anything else that's constant? Lots of Fs, and we have a lot of Fs here. 8 1s and Fs kind of mixed around. Got a 7F, followed by some 7Fs, 8 1. I think this is correct. I think we're now looking at the data here. So I'm going to put this in a loop, and we're just going to continuously loop through this. So display info and jump short dot display info. I might not be able to do a short jump anymore. If we can. Now what this is going to do, this is going to do a live updating screen. So I'm going to quickly hit the head, and I'll be back in less than a minute. Alright, so now this is live updating, and we've got a few fields here that are twitching along. So, I'm curious if these are temperature related or anything of those like. So, looks like we're starting at 20 is the one that's kind of twitching around. So that's apparently the 2.5 volt signal, and that's kind of staying in a tight range, so maybe that is correct. 1.5 volt VCC is the next one. 5 volt, then we have the 12 volt kind of switching around, and actually that one seems to be bang on in terms of 12 volts is B, or no, C, and you can see it's kind of fluctuating in that B, C, D area. Then the next thing is the temperature on zone 1, then we got a zone 2 temperature reading. Now, that's definitely wrong because that's saying something negative. Negative 15 degrees. Don't think my processor's at negative 15 degrees. Then we've got this 2C and OC flipping back and forth here. So I'm not quite sure what's going on. But I think we are in the right area. Let's quickly open up IDA and make sure there's nothing else that's doing very similar stuff. This is jumping to DI, so that's the return. And where's this actually getting called from? Let's set this as a function. And yeah, it's jumping there, but then it's going to return into CBD4. So I just doing that wrong essentially, but no XREFs there. But there's definitely data here kind of twitching around us. This does look like it could be the live data. So one of the things that I might do is I'm going to go in here, I'm going to open the computer, and I'm going to put my finger on a fan and see if I can ooh, oh, it might hurt. I don't want to break my fan though. Sadly, there's guards on all these fans, so I can't stop them. But I want to be able to see if any of these fans can be stopped, but it doesn't seem like I'm going to be able to reach those without potentially breaking one. So I'm very curious what these fields are. So these temperature zones, apparently the way that the temperature zones are used. So let's go to hardware monitoring. What's this one? I want to find more information on these fields. So let's go find the register reading at nominal voltage. At maximum voltage, at minimum voltage. So actually, the voltage ones are going to be in the C range, C0. So looking for C0s or anything fluctuating in the C0 range. And there's these CFs, and power is probably going to be pretty constant. So maybe these CFs are the three, I don't know, but there's more than that. Is there an AE anywhere? I don't see one. Frustrating. Okay, now these guys, how do these temp readings work? Current temperatures of the internal and remote diodes. They are represented as 12-bit. What? Current temperatures are represented as 12-bit 2's complement signed numbers in Celsius. What? Where are my other bits then? Because this is 8 bits. Stealing my bits. Table 24.3 shows the conversion for the 8-bit reading value shown in these registers. The extended precision bits are accessible in the 80. Okay. Temperature reading will return a value of 80 if the remote diode pins are not implemented by the board designer or are not functioning properly. Okay. Registers are read only. Yep. And zone 1, 2, 3. So basically, yeah, we'd be looking for something in the normal hex range. So I mean, this is like 20 flopping around it. These ones kind of seem like they might make sense for temperatures. And it looks like, so you got this followed, we got a twiddling bit followed by something that's not twiddling, twiddling bit, something not twiddling, twiddling bit, something not twiddling. And same up here, this 26 kind of moves around a bit as well. So then we have these fan tachs, and that might be what that is actually. Those might be the fan tachometers, because those are actual words. As you can see, there's a low and a high part. So the low part's what's fidgeting around, and what it could be is that's at 3C. Oops. We want 10 or 013C. That'd be 316 RPM. It's a little bit low. Oh no, that is 10. 10, let's say 3C, or yeah, 10, 3C. I would say 4156 RPM, which is insane. So that doesn't seem right. But what I can do is I can actually just pull one of these fan headers. So let's see what happens here. I'm gonna pull this fan out and watch for anything to drop to 0 or Fs or something along those lines. Okay, I pulled out that fan. Oh, there we go. We got all Fs. See all the Fs up here when I pulled out that fan? So I think that is definitely fan thing. So I'm going to pop that fan back in. We'll see if those go away from Fs. And there they go. And there's two fans that I unplugged because it's a dual fan unit. So, and those are actually spinning down in RPM. They started very high and now they're spinning down. The number's going up for some reason when they turn down, so let's see how this works. So these are actually, is that 20? I think these are not at 20 and I'm just counting wrong. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So there's 19 per row. So that's 19, which means 19 times 2, 38. So that is 38 that we're looking at, which is 26. This is close. So this could be... These are definitely the fan speeds. So we found where we want to be. Oh, that's interesting. So now we got those fan speeds, and it seems like we have more tacks than. So that was 2. I did 2 fans there, and I've got a total of 5 fans on my machine. So I'm going to pull another fan here, and I'll see what happens. So this is on a secondary CPU. Oh, fucking hell. Come on. Anything go to Fs? I didn't see anything go to Fs. Anyone see anything go to Fs? We've got 1, 2, 3, 4 twiddling away. I didn't see anything change. I'm going to plug this back in if I can. Fucking light. So that fan comes back online. So, I don't know, I didn't see that one. But those are the CPU fans that I unplugged. So maybe it's only the chassis fans that are going to flip around. So I've got another chassis fan here that I can pull. It's just a single one. And let's see what this one does. There we go. So we got 2 more Fs here. So these 3 are definitely fan readouts. So if I plug this back in, we'll see those numbers under the cursor come back. So there we go. Okay. So those are definitely fans, and fan tachometer readings contain the number of the number of 11.11 microsecond periods between full fan revolutions. So they produce 2 tack pulses per revolution. These registers are updated at least once every second. Each fan is 16-bit unsigned number. FFF means the fan's not spinning or it's not connected to a valid signal. Then we have the duty cycles. These are only writable when it's in manual mode. So these are probably just the ones directly following. 1, 2, 3 fields. Are these changing at all? I don't think they are. So we're let's see. So that, and then that. Yeah. Oh, those could be 4 readings, or maybe the, actually, it's 28, 29, 30. So it's according to this spec, you get the, oh no, these are all just in order, never mind. Then you have 30, so directly following it, you have all the values. So here we have these twiddling away, and let's say that one's another fan as well, and 1, 2, 3, 4, 5. Could that be? Those are the 5 speeds. Potentially. So let's see. PWM duty versus register reading. So FF is 100%. So what if I just went to those bytes and changed them to 100%? Although it's not in manual mode, is it? Device ID 8C. Where's that at? Well, that's probably different for this. Then we have 5C is the company ID. Anyone see a 5C? I do not see a 5C. Going crazy. I don't see a 5C. Fuck it. Revision. Ready lock start. So that is at 40. Interesting. So, what I'm thinking is that I think that this maybe is a 5. I think this computer might have 5. Yeah, I know this computer has 5 fans. I've got 1, 2, 3, 4, 5. 6. I technically have 7 fans. So I have 5 on the chassis and 2 on the CPUs. So maybe this upgraded model has 5. So it could be that this is one reading, this is another, this is another, this is another, this is another. So I verify that these 2 go, this one goes. I can pull the memory fan right now. Let's do that here, and we'll see if one of those drops. Come on. So we've verified that 3 of them drop so far, and that is my intake and my output. Did anything drop to Fs yet? Not yet. I unplugged my chassis fan, or my RAM fan, and nothing has gone to Fs. So this RAM fan might not actually be controlled with that controller, though. It has a different pin. It's not connected like to the motherboard in the same way. So if we put that back on, so we've seen 3 working. I've got one more chassis fan that I want to test. How the shit does that connect? There is no connector going into that fan. It is a magical fan. Oh, there it is. Okay. So that's another chassis fan. And if I pull this one, what happens? Come on. Come on! Ah, you bitch. Fuck. Okay, come on. That's a really awkward angle to get my hand in there. Ah, shit. There we go. Anything else go to Fs? Anything go to Fs? Oh, we got these 2 that went to Fs here. So I'm going to keep my cursor on them and see if that comes back. Oops. Put that back. And there we go, that's giving readings. So, we have confirmed at least 4 fans are operating on this. So, this specification only mentions 3 zones, and we know we have more than 3 zones. So, so I think we definitely are not going to be able to use these offsets. So we're going to need to find, given that this was already organized in a way that it was just directly followed by the controls that you wanted to give them. So we've confirmed there are 4 fans, 1, 2, 3, 4 that we are able to control. And then there happens to be followed by 1, 2, 3, 4 fields. and those might be the duty cycle thresholds. So let's find what those offsets are. And so, how many did we count here? Was it 19? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Oh, so we're getting 20 per. Yeah, that makes sense. So this is 40. So this is the 40th one. And actually, no, this is the 40th. This is the 41st. Yikes. That's ugly. Am I doing my math correct? No, this is address 40. Yeah. So if we go 40 and convert that to hex, we get 28, which happens to be where these fan tacks start coming in. Then we get 29, then we get these, then we get this, then we get this. So I think we just have another fan on here. So this supports 4 fans. And then you can see here we have 1, 2, 3, 4 fields before we have Fs. And here we have 1, 2, 3, 4 single byte duty cycle fields. So if this is 28, then we are going 4, 8 ahead. So this is 30. So at 30 is where the PWMs start. Wait, that's where this is. Oh, look at this. Look at this. E and F are missing. So this starts at 30 again, and then I bet it goes right to 30. Yeah. So basically, I'm just going to write Fs to those areas, to the 30 through 33, and see if that turns up my fans. And maybe that's just all I need to do, because it might already be in manual mode. So let's go through here, and we'll do a move into... so we need to do this. We need to select the port OX30. We need to do that in line. Move AL OX30. And then we're going to write FF to it. So we'll inc DX out DX AL, move AL OXFF. So this is write FF to there, write FF to there, to 31, to 32, and to 33. And then we have to move this above my loop, otherwise this will never get executed. And then, boom, 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 boom. There we go. So let's build that, shut it down, boot it back up, and hopefully our fans go fucking crazy. If not, we just need to set that, if not, then we're just going to need to set and find the manual mode field, and that will be very difficult to find, but I think we can do it. So, in theory, this thing just hopefully just launches right now and just goes. So, and we'll verify that the F show up here. Oh, they did not persist. Did I write those correctly? To 80? I'm reading from 80. I'm writing 30, outputting 30. Then I'm incrementing DX. Then I'm moving FF and I'm writing that. And that's not staying. You can see these values are not holding. And what do these say? Read write note. These registers are only writable when it's in manual mode. We're not in manual mode. Mother of shit. But I think that's definitely a sign that these are the fan speed things, because otherwise they probably would have written. So we need to find manual mode here. And manual mode is test mode. Manual mode is when the start bit is set to 1 and the lock bit is set to 0. The current duty cycle registers are writable to control the PWMs. When the lock bit is set to 1. Okay, so we need to find, so that's the start lock thing. And I think we actually know that field, don't we? It's 40, isn't it? And we know that because that was the first thing it wrote to, is ready lock start. And basically we can look for 40, so we are at, so this is, what did we say that was? This is 30. Is it? Wait, which one's 30? This 30. So this is 34, 38. Then we come down to the next line. This is 3C. So what are we looking for? 3C here, and this is 40. And this is in 5. So there's currently a 5 in there, which would say it is ready and started, but not locked. So it's usually it starts in state 4. And that's kind of what we think is what is being written in there, because if we look at what our BIOS is doing a write to, it's pulling up the 480 and it's doing 40 and it's writing a 4 to there, which is the default value, which makes me believe that this is correct. So, that's a 5, which means it is ready, not locked, and started. So let's go down to the lock. Lock and start bits are locked by the lock bit. The override bit is always writable when the lock bit is set. Okay, so the lock bit isn't set unless that offset's wrong. Is there anything in here that's 4 or 6? I don't see anything that's 4. I mean, that makes the most sense, because that's the field we're writing. We write it as 4, and then it goes into the next state. So we're going to search for more information on that field here. Ready lock start. Oops. Yeah, lock start monitoring. Here we are. This is lock bit is cleared when that's asserted. The start. When software writes 1 to this, it enables monitoring and PWM output control based on the limited parameter registers. Before this bit is set, the part does not update register values. Whenever this bit is set to 0, monitoring and PWM output controls are based on the default limits and parameters regardless of the current values. It preserves these and is stored. When the bit is 0, all fans run at full 100% duty cycle, i.e. PWMs are at 255, low for 1 clock. When bit 0 is set, the part is not monitoring. Or when this bit is 0, when this bit is 0, okay. So let's clear that bit. So let's go up here, let's write into, what is this? This is 40. So let's write a 4 into that. And now that's already what our OS is doing, or our BIOS is doing. It's writing that 4 in there, but it might be writing that 1 in there later. So we're going to set that start bit to 0 by writing that 4. So then it will be in a state of ready, and we can actually do override as well, but we'll do 4 for now. And then we'll put override, because override also mentions that it just puts everything at 100%, whether it's set or not. So let's see what happens. So that is now set to 4. These fans are definitely not at 100%. So maybe that's not the right field. Maybe that is not the right field. Oh, 1D. Isn't that the device ID? Oh, no, it isn't. 5C. Never mind. The other thing is we can look for that 5C, but we looked for that before, didn't we? Yeah, we didn't find it. Here's another 4, followed, there's a 1E before that one. That would be the revision. And then there's a 4, and then it's followed by a 0, which is interrupt status. But the thing is, the lock bit's not set, so we actually would want to find a 6. 6 is what would represent what we're seeing with that lock bit being set. So we can write that override bit, which is bit 3, so 0, 1, 2, 4, 8. Oh, really? 1, 2, 4, 8. So if we put that at 4 or OX8, now it's override non-locked, and let's reboot again. Otherwise, I just think that this is just not the same field, and I mean, we're definitely seeing those PWMs coming in, and those are at the same addresses, so I think that's correct. I mean, the fact that the first thing it's writing is to that 40, and then what does it do? It writes to 33, it writes an F to 33, and 33 is, 33 is the, I hear fans. I think we did it. I think we got it. So we put that into override mode, and now we can see that these are set to Fs, except for the last one, which is set to OF, which is interesting, but maybe that's the max on that. Maybe it's like a smaller fan, and all it can go up to is F. Because we can see it explicitly sets 33 PWM to F. And then it goes and sets FF to, yeah, whatever. That's like the test, I guess. But our fans are running at full right now, so I think we got it, guys. So let's drop these guys from Fs to something else, and see if we can get those controlled. God, that's fucking awesome. So that one's at full. 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 The CPU fans are at the same speed, but I don't think my CPU fans actually are controllable. No, they definitely are, but they're probably, you do those through Intel. Okay. So you can see these guys are running at a lot higher values than they were before, or lower value. I don't fucking know. So that guy's running. And so let's see if we can drop those down really quiet by setting these to 1s now. So let's drop these to 1, 1, 1, 1. And send that through. Oops, almost disconnected my mic. We'll turn this off. And, oops. Get that turned on. And, when this boots up, hopefully the fans, since we put it into override, that sets everything to full. And I wonder if, where were we? PWM current duty cycle. So have we booted? Not yet. Yeah, we're still at full. So that that override setting is doing exactly what it's supposed to. So that. Wait, I wonder if that's 6. No, that's definitely the low. Let's see what the ordering. It does the low byte first. Yeah. Okay. Now, luckily we've accomplished what all I want to accomplish, which is being able to set it to high, but I would like to tweak those. So we're definitely setting that override bit correctly, and let's go check out that lock bit. Setting this bit to 1, lock specified limit and parameter registers. Once this bit is set, limit and parameter registers become read-only and will remain locked until the device is powered off. Becomes read-only once it's set. Override means I can wipe that bit, but as you can see, I'm running at C, which is override and ready, but nothing else. But I still want that manual mode. I feel like there's probably another thing to get that into manual mode. But let's go through and find temperature monitoring, low power temperature measurement. So, just turning that off so it's not as loud. Okay, interrupt signal, low temperature measurement, fan control. Okay, so we got the 3 zones. In ours we have 4 zones. And then we have these, which are the minimums for the tax. Oh, are we just arbitrarily setting shit that probably is unrelated? Uh, shit. Okay. So these are the TAC minimums. So 54 through 5B. Let's go find where these are written up. Fan speed control, PWM 1. Manual mode, this is... Okay, here's what, yeah. Just putting into, to control PWM outputs in manual mode, set the mode to operate in manual mode. Write 1112 bits 7 through 5. Didn't it say that like completely elsewhere that it needed to... Oh my god. The speed of the fan is controlled by... The duty cycle must be programmed in there. So all I need to do is set these 3 bits. And I'm going to put those in 5C and 5E in PWM X. So 5C through 5E, and I'm sure it's through 5F for me actually. PWM X configuration. Let's find this. Come on. Fuck. 5CH. Where are we? 5CH. 5F. Oh, interesting. So I'm curious where our zones are. Because we have the 5. So we definitely are ready, lock, set. Yep. Current duty cycle, and then we have the fan tax, and then this was reserved. But how do I set PWM 4? That's where it's interesting. PWM 1 configuration 2, 3. I'm wondering if they shift it down, so 5B through 5F are what it uses. So since they're reserved and they're read only, I can hit them anyways and just see what happens. So what we're going to do is we have to OR those top 3. So we're going to do, we don't need override anymore. And so these will set the zones to all Fs. And then we're going to do more of this shit, but for these zones. So let's do 5 for the configurations of the zones. I'm curious how this is going to work on mine. I'm actually just going to dump 5A and above on this, just to see what it looks like. Currently CA, so 5A. And we're going to boot this up, because you see we have these like PWM 1, 2, and 3, but we have 4 PWMs that, we might not. We might not, actually. This guy is going to boot up, and we're going to write from 5A, and we'll see if we see 0000626262. And if that's the case, then we're just going to have to set those high bits. Okay, so 7869 CF, CF, CF. What's CF? So that's going to be 1100. So Xeon 2, Xeon 1, that's off, and then all these are on. I think those are still correct. So we're just going to set that to DF, essentially, right? Or EF. So we'll set all those zones to EF and see what happens. Okay, so here we write all the zones. And here we're going to put, before we do that, we're going to put these into manual mode by writing 5C. And that's this. And I don't think this third one matters, because that never gets set. So 5C, then we have DE, 5D, 5E, and we're just going to move EF into these guys. And then, so now we're doing we don't have it in override, and then we just set all these to EF mode, and then we set all the fans to full speed. And then if this works, we'll try it with no speed, and if that goes through, then I think we're done. Okay, so our fans are quiet. They're actually like, oh no, they're just on very low. So that's strange. So we set those to EF. So let's look for 6.2, because those are what those are supposed to be at. 6.2s, I don't see any 6.2s. Those made sense being where they were. And we are in manual mode. That's what it said, right? Put it into manual mode, do that shit. Yep, set those in 5C through 5E. Sets 111. And, yep, duty cycle must be programmed in 32. And we're doing that. Bubkiss. So, auto limit condition occurs, blah blah blah. Auto fan. Connect to testing fans, thermal zone 2. Anytime the temperature of a zone exceeds something, all PWM outputs go to 100%. Duty cycle to provide maximum cooling. If the start bit is set, the auto fan control block will evaluate the temperature of the zones configured in a round robin. It will evaluate the zones at the maximum of 0.25 seconds. So we have the start bit. Do we not want the start bit? Well, shit. Well, shit. Temperature reading. PWM crap, and more crap, and here we go. If we have the ready, if the start bit is set, it enables monitoring in PWM. If it's off, all fans are on full 100% duty cycle. So we're setting that to 4. Is that a problem? Let's set it to 5. So I'll set it to ready and start. And we'll see if that changes it. Because otherwise it should be at 100% according to this documentation. It becomes read-only when the lock bit's set. And let's drop this down to 0 now, so we can get the whole shebang. Come on. Come on. Come on. And nope. So we've got these guys. Oh, they're spinning up. It's spinning up. You can see these numbers going up. So you can hear it slowly spinning up. And now those are all maxed out. So I'm assuming what happens is by writing these Fs, it actually, I write the Fs and then it displays what it's currently set to, and then it slowly ramps to that position. And we don't want it to ramp, so we're gonna kill this guy, and we're gonna bring him back up, and we're gonna put him on zeros, and let's see what happens. I'll put the fans to 1, and we'll see if they spin down. So it seems like that auto mode seems to have some sort of sweeping shit. VBAT, blah blah blah. Startup sequence. Start bit 1, then fans are... Yeah, you can see those are spinning down. So that's what it is. I do have full control of the fans now. But I don't like how slowly they're changing speeds. Look at this, these fans are gonna go almost all off. Yeah, they're off now. They're at their absolute lowest speeds. That's awesome! Okay, so I've got fan speed control now, but it gradually occurs. So I'm assuming that might be part of the these EF control structures. So if we look at that, those are at 5C. PWM configuration, these, okay. So the zone and the mode, so we put those in full manual mode. Those become read-write. It's possible by writing those, yep. And when the fan is disabled, and then full on, it's driven high or inverted. And, okay. So fan manually, controlled by the hottest zones, fan on, zone 1 auto. Okay. So what were they at? They were at DF. So what's D? D is going to be this. Fuck. What? Were they on CF? Yeah, they're on CF. Never mind. So that was 110. So they're on controlled by hottest zones 1, 2, 3. Okay. Now, then we have the next bits. For spin up enable, spin up. Specify the spin up time of the fan. When a fan is being started from the stationary state, the PWM is held at 100% duty cycle for the time specified in the table below. Okay. So we currently are setting it to spin up of... We're setting it to 4 seconds spin up time. So if we change that to 0, because fuck it, do it, then we can change that. So we're writing EF. We want to get rid of boom, boom, boom. Now we want to write E8. And what we should find, if we write E8 to these, and then we write Fs to everything else, that this thing will just fucking launch immediately. So this time it won't spin up, it will just go. I don't know if that's a bad thing or not. Is the spin up good for the fans? I don't really give a shit. Disabled, all the fans go full for the duration. Yeah. So, what are these? Temperature, PWM frequency? Can I like overclock my fans? Oh, they're still ramping up slowly. And do we have those? Yeah, those are written as E8s. Fuck. Spin up time. In the spin up register. Yeah, spin 2, 1. SUEN? What's SUEN? Spin up enable? Force spin up enable. Oh, fuck that. Let's kill that too. E0. So E0 is spin up is disabled. Just fucking launch my CPUs to the moon. Let's do that. Dun 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 dun. And hopefully these just go FC EO EO EO, and all it. Yeah. Let's see. Come on. What is that? EO is just those top 3 bits set. What's that 4th bit? INV invert. PWM invert. Inverts the PWM output. It's still ramping slowly. If set to 1, 100% duty cycle will yield an output that is low for 255 clocks and high for 1 clock. Set to 0, 100% duty cycle mean that output is high for 255 clocks and low for 1 clock. Okay, yeah, that's what I want. So why is this still ramping? So we've got these zones here. And these guys didn't quite go to full speed. I don't know what that OF is, actually. I guess we can look that up, because apparently... yeah. The thing is, we have four fan outputs, don't we? 1, 2, 3, 4. Yeah, we have 4 fan outputs, but we only have a few controls. So I don't know why it's taking time for that to scale up. That's a little bit of a frustration. Not that it's a huge problem, I can have that ramping, but it doesn't do that in the BIOS when I change it. This feature, to reduce spin-up time, the device has implemented spin-up reduction. Uses feedback from the tacks to determine when each fan has started spinning properly. Spin-up for PWM will end when the tack reading is when it's below the minimum or the spin-up time expires, whichever comes first. All tacks associated with PWM must be below min for spin-up to end prematurely. This feature can be disabled by clearing bit spin-up SUREN of the configuration 7F. What? I thought that's in here. SUEN 1, 2, 3. Interesting. If disabled, the fans will go on full for the duration of their associated spin-up time. Note that the TACX minimum registers will be programmed with a value of less than FFFF for the spin-up reduction to work properly. Oh, I see. Do I see, though? To reduce spin-up time, bits 2 and 0 specify the spin-up time of the fan. When fan is being started from the stationary state, the PWM is held at 100% duty cycle for the time, blah blah blah. Interesting. Forced spin-up enable. Enables forced spin-up option for the PWM. If set to 1, the forced spin-up feature is enabled for the associated PWM. If the set to 0, the forced spin-up feature is disabled for the associated PWM. Okay. Huh. Interrupts will never be generated if its minimum is set to that. Register become read-only. Well, they're in manual mode. And so we got them running there. And doesn't seem like it's as fast as when they're in just full-on mode, but they're still pretty good performance-wise. So this is the temperature limit PWM output minimum fan speed. That's the PWM output at 100% duty. And it spins up over that time. Maybe there's another field I have to set. So maybe I have to go and... oh, ramp rate control. What? So what is the spin-up shit? I don't even know anymore. Ramp rate control. There's only 2 ramp rates. Register become lead only when the lock bit sets. Any further attempts to write these will have no effect. Res 1, writes are ignored. So ramp rate control. Instantaneous temperature spikes may be sampled. Oh, I see. This ramp rate control logic changes the amount of PWM over a period of time. So ramp rate time in seconds. So if it's set to 1, time per PWM step is 5. Minimum PWM duty cycle. PWM ramp rate, hertz, 200. This is what we want, right? Just fucking more bits. So res 1, res 1, res 1, res RR1E. What the hell does that mean? Res 1. RRX. RRX. Okay. 2 to 0. RRX 2 to... What's E? So I'm assuming this is the ramp rate for the first zone, this is ramp rate for second zone, this is for the third, and this is enable the ramp rates, and these are all reserved. I see. That's what it is. Okay. So the default value, E0, which is the slowest ramp rate. And we want to put these at RR1. Okay. What does enable mean, though? Does enable mean good or bad for us? Okay. Ramp rate control limits. RE enabled a ramp rate control for PWM 123. So I guess we'll put them at 4 for everything. That will enable the ramp rate control and also put them at fastest speed. Time from 33% duty cycle to 100% duty cycle. Fast. That's what I want. So yet another bunch of fields we have to set. It's just 2 fields, I guess. So we want to set 64, I think. No, 63 to FF. So it enables everything and puts everything high. And then for the other one, we want to do EF, because it wants these reserved to 1, and then we'll set these all high, and that's going to be at 62. So once again, we will kill this guy, start him back up, and hopefully that fixes our ramp rate problem. So, okay, BIOS takes over. Premium duty cycle. That's the minimum duty cycle. No temp limit. Okay. So let's get it booting. And hopefully it just ramps. Oh, that's even slower. Oh boy. Oh boy, that's really slow. Did I go the wrong way? Do I want 0? PWM ramp time in seconds. From 0%. Yeah, I want 1. Which should, in theory, ramp from 0 to 100% in 1.2 seconds. And this is the opposite of that. Limits the amount of change to PWM duty cycle over time. So what if I do these... Oh wait. Why did I do E0? Oh no, that's what I want there. EF. So this will be 0. We'll make this 0. Oh, that's what we were though. It has to be 88. That will enable it, and then have it at 0. And then this will be like super slow. So, let's see. E8, 88. That will, yes. That will enable it, but it will keep them at 0. But this is saying that 1, setting all the 1s is like very fast. This assumes the ramp rate enable bit is set. Fuck. Do I need that too? Okay. It seems to be ramping just as slow. Ramp rate control logic. For detailed description, go to those bits. Yep. Yeah. Yep. Autofan calculates PLM. Register. Okay, and running at full. Zone 1, limit, minimum duty cycle. Do I need to set the minimum duty cycle for these guys? I'll do that. instead of doing this ramp rate change, I'm going to set the minimum duty cycle to FF. And that will set them to, yeah, FF is 100%. Maybe that's how you bypass the ramp rate, is by going pure on these guys. Let's do FF on that, FF on that, and let's change this to 64, 65, and 66. So that will set my minimum PWM duty cycle to max on those, and what comes after that? Directly 67, so temperature limit. So instead of saying, hey, I want the fans to run at full, this will say, hey, the fans need to at least be running at full, so maybe it will immediately jump to that. And maybe that's the proper way of doing this, and I don't even need to set them up here for the individual fans. So we'll see what happens. Boot, 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 boot. Come on. Still ramping. How is that happening? Registers become read-only. Any attempts to write them has no effect. Minimum duty cycle. Measured by the temperature limit in the... So let's see what these ramp up to. Because they would stop at a certain level to see if these go to pure FF. I wonder if they will. I want it to FF. That, okay, EA. FFF2. I guess those are the maxes for those. Absolute temperature limit. Test registers. Special function. Bit decoder. Interrupt. Attack PWM association. Interrupt register status SMSC test. Test. Fan. Okay. Any further? 0. Force tack reading register. Okay. Edges. PWM option. Tacks reading are updated once a second, twice a second, every 300 milliseconds. Snap to 0. This bit determines if the output ramps down to off or is immediately set to 0. Step down of the PWMX output to off at the program ramp rate, or 1 transition to off immediately when the calculated duty cycle is 0. Default. Okay, snap to 0. Guard time, opportunist, okay. Voltage shit. Load register. Test. Temp. It's frustrating that those ramp, because the BIOS is setting, when you set them in the BIOS, they just immediately go to what they are. So I'll do ramp rate control logic. Tack reading greater than tack limit. Spin up time. Okay. So, tack reading versus tack limit. And spin up reduction is enabled, SUREN. The spin up time will be less than or equal to the program time for spin up. Once the tack, whatever, blah blah blah. If this feature is enabled, this feature defaults to enabled. It can be disabled by clearing bit 4 of the configuration register 7F. If disabled, all fans go to 100% duty cycle for the duration of their associated spin-up time. Note that the tack must be programmed with a value less than that for spin-up reduction to work. So, have we tried that yet? 7F? So let's go to find 7FH. 7FH. And find where that is. 7FH. Configuration. SUREN. Let's turn that bit off. So let's okay, so we've got our this stuff. So here's where we set the fan speeds, here's where we set them to manual mode, here's where we set it to started and enabled. So here let's we have got this 64. This is going to become 7F, which is configuration. We're going to output that, and then we're going to, now that we've set that, we're going to in al dx, and then we're going to and that with the inverse of 1 shift by 4, so bit 4. So mask off anything that's not bit 4, and then output that to dx. So this should globally disable that spin up bullshit. It's funny how many bits are everywhere. There's like, 50 bits, you've got the global enable, and you have like a bunch of other enables that don't seem to do shit unless, I don't know. So, put all the fans in manual mode, then we output 7F as the thing we want to write, increment dx. In dx, that will read that reg, and then we'll clear that bit, which is bit 4, and then we will output. They're still ramping. That makes no sense. That makes absolutely no sense. Oh my god. Interrupt enable. Let's go search for more spin up. Let's go top and search. Spin up reduction enabled. Hottest option, ramp rate control logic. If enable limits the amount of change in PWM duty cycle over a period of time. This period of time is programmable in the ramp rate. So that's the spin up time. Then we have the ramp rate. Control disabled by default. Yeah. Auto fan determines the duty cycle. When it's disabled, the PWM output will be set to that calculated. Yep. And that's what it is by default. And we checked that before. Output transition. When generated by the auto fan control, transitions from the off state to the on state. The internal PWM will ramp is initialized to the calculated duty. Any ramp rate in PWM X current duty cycle is at this value. The PWM output will latch the duty cycle in the ramp rate. Okay. Output transition on to off. So these are the RRX things that we were looking at before, and we set these, but calculate duty cycle. So there you go. That's exactly what it's doing, and PWM ramp rate control. 26 milliseconds. Wait, what is this? PWM frequency at 11. PWM frequency at 87. PWM ramp rate at equals 38 hertz. So if I change the PWM frequency, 26, 26, 26. So same ramp rate, and that's at a 26. Yeah. But I thought by default this is none. That's saying how long should it take? It should take 4 seconds. Ooh, 6 seconds for that. That sounds about right. But we tried this RRX shit. Did we not? Did we do this wrong? RRX. There's the ramp rate. Here it is. This is in the... Yep, those things. Error X. No, this assumes that RRXE is set. Yes. Oh, I see. If it's not set, then what? Is it instant? Because we tried that. We tried having that not set, and it didn't work. Well, we have control now, and that's actually just good enough for what I need. I'm going to probably be just turning it full on, full off. Let's see, fan TA, interrupt enable, error shit, fan tac, yep, PLN option 1, 2, 3. Cool. So, I mean, I got what I wanted. The ramp time is a little bit frustrating, but quite frankly, 4 seconds doesn't really matter when I'm spinning up things. So, I guess I'm probably gonna end up this stream now, and yeah, that's about it. I hope you guys enjoyed it. It was a pretty long one, but got to do some reversing, got to read some specs, got to do some osdev. All of it was 16 bits. I don't know, it's kind of good fun. It turns out the spec was more accurate than we were expecting, but we still needed to reverse the BIOS to figure out that it was 80 instead of 70 for that one offset on the 400 field. So it was kind of cool. It was a good example of getting into some BIOS dev or BIOS reversing. So hope you guys liked it. It's kind of what I've been up to, and I'm probably gonna write a driver for that for Windows so I can have my fuzz range fan controlled manually. So I hope you guys liked it, and let me know if you did. So let me know what you did or didn't like, so I know what to change in the future. And you can always follow me on Twitter or whatever. So I should start whoring out my Twitter, because people always ask me, where's the stream? I didn't see that there's a stream, and I announce all these on Twitter. Usually I try and announce them an hour early. Today I announced it like 3 hours early, so it gives a little bit of time for people to catch on. So I'm on Twitter's at Gamozo Labs, GAMOZOLABS, one word, no underscore, no space. That's it. So hope you guys liked it. I will be around probably later this week. Bye-byes.